A gigantic invisible monster lurks in the dark, a cliché born from our deepest fears of the unknown. It devours stars whole. It warps the very fabric of time. It swallows everything that strays too close, even the unblinking speed of light. But that picture, that simple story of a cosmic predator, is just the surface. The real story, the one that unravels our understanding of reality, begins only after you fall in. These cosmic objects are not empty voids, not simple drains in the fabric of the universe. They represent the most complex, most mind-bending phenomena known to science. Inside them, space stretches into an infinite thread. Time shatters into a million different futures and pasts. The fundamental laws of physics, our trusted guides, begin to whisper secrets they refuse to reveal anywhere else in the cosmos. This journey is not for the faint of heart. We will dive headfirst into theoretical infernos, quantum firewalls that might incinerate you before you even cross the threshold. We will explore tangled time loops where the past and the future blur into an inseparable knot. We will touch event horizons that may be nothing more than holographic projections of information. We will confront singularities that, according to some of our best theories, might not even exist in the way we imagine. Inside, the very essence of space could spin like a celestial tornado, dragging you along for a ride you cannot escape. Time itself might reverse its arrow, showing you the effects of your actions before you even take them. Echoes of quantum chaos could ripple outward from the core, the final frantic heartbeats of a dying reality. Some of our most elegant theories suggest you will never truly reach the center of a black hole. Others propose that your very act of falling in will birth a new universe, a new beginning spawned from your end. Still others suggest a stranger fate. You might witness your own past played back before your eyes, a ghostly projection on the interior of the void. Or perhaps you will simply become a smear of information, a ghost of data painted onto the surface for eternity. These are not metaphors. These are not flights of fancy. These are real, tangible possibilities derived from the rigorous mathematics of our best physics. So fasten your mind, not your seatbelt. This is a fall with no bottom, a plunge into the strangest, most beautiful, and most terrifying corners of the cosmos. Welcome to the inside of a black hole. The event horizon is not the real boundary. Most of the time when we hear the term black hole, we conjure an image of a cosmic trapdoor, a portal that leads to absolute nothingness. That so-called point of no return, the place where even light is doomed to disappear, is the central feature in that popular picture. Many people, even some scientists in casual conversation, describe it as a sharp edge, the absolute precipice of gravity's inescapable grasp. But this is a convenient lie. It is a simplification shaped more by our limited, distant perspective than by the subtle and strange truth of the universe. There is no wall at the event horizon. It is not a physical surface you could bump into. In a very real sense, the line is not always even there. It is a mathematical trick, a moving ghost line that changes its appearance depending entirely on where you are standing. If you are a distant observer watching from a safe corner of the galaxy, it certainly looks like things falling toward a black hole slow down as they approach the event horizon. This illusion is a product of extreme gravitational time dilation, a warping of time itself. The image of the falling object stretches, its light reddens and fades until it appears to freeze in motion at the very edge, never quite managing to cross over. But if you were the one falling, you would feel nothing special at that moment of crossing. There would be no bump, no warning siren, no jolt to mark the transition. For you, the journey would simply continue uninterrupted. That paradox, the stark difference between the outside view and the inside experience, is at the very heart of general relativity. It is also the point where black holes begin to force us to question our most fundamental ideas about space, time, and the very act of observation. For this profoundly strange reason, physicists say the event horizon is observer-dependent. From a great distance, it appears to be the end of the road, but when you are the one on that road, it is just another milestone on the journey. It is like the horizon here on Earth. When you stand on a shore and look across the ocean, the sky appears to meet the water in a sharp, definite line. But if you try to sail to that line, it recedes with every nautical mile you travel. You can never reach it because it is an artifact of your perspective, not a physical place. The event horizon of a black hole does something similar, but this time it is space-time itself that is changing shape around you. This is not just a strange quirk of physics, a mere curiosity. It has profound and deeply unsettling consequences. Take Stephen Hawking's famous prediction that black holes emit energy. The principles of quantum mechanics state that pairs of virtual particles are constantly popping into and out of existence everywhere in the vacuum of space. Near an event horizon, it is possible for one of these particles to fall in while its partner escapes. From our distant vantage point, this makes it look as though the black hole is slowly radiating energy and shrinking, a process we call Hawking radiation. This process itself suggests the event horizon might not be as solid a concept as Einstein first imagined. It could single-handedly rewrite the laws of thermodynamics, challenge the conservation of energy, and perhaps most importantly, threaten the sanctity of quantum information. If information can leak out of a black hole via Hawking radiation, we are faced with the so-called information paradox. Does the black hole ultimately erase the unique identity of every star, planet, and particle it consumes? Or does that information somehow survive, perhaps encoded in the escaping radiation, or tattooed onto the event horizon itself, quantum? Physics is built on the bedrock principle that information can never be truly destroyed. Yet black holes seem to present a direct and violent challenge to that rule. And this is where things start to spiral into even deeper uncertainty. If the event horizon is merely an illusion, or worse, if it does not exist in a stable, unchanging form, then we may be misunderstanding the very nature of the black hole. Some physicists speculate that the event horizon might conceal a violent secret, the firewall. This radical and controversial idea proposes that instead of a smooth, uneventful ride past the horizon, an infalling observer would collide with a wall of incredibly high-energy particles. It would be a quantum inferno, a fiery barrier that obliterates you instantly upon contact. This violent end would protect the rules of quantum mechanics at the cost of shattering general relativity's prediction of a gentle transition through the horizon. It remains one of the most hotly debated concepts in modern theoretical physics. As of today, no one has found definitive proof either for or against its existence. If the firewall is real, our mental picture of falling into a black hole, a journey that starts calm and ends in chaos, gets flipped completely on its head. Furthermore, let us not forget about black holes that spin. These objects, known as Kerr black holes, twist the event horizon into a more complex and fascinating structure. A spinning black hole creates an outer shell called the ergosphere, an oblate region shaped like a flattened sphere. As the black hole spins, it literally drags the fabric of space along with it in this swirling region. Inside the ergosphere, standing still is impossible. You are forced to move with the current of space-time. The event horizon is no longer a simple boundary, but a component in a much larger, more complicated dance between gravity mass and angular momentum. Yet, even from this more complex perspective, the notion of the horizon as a clear, definitive line continues to fall apart. Deep inside the black hole, past the classical event horizon, and even beyond the whirling whirlpool of the ergosphere, lies the singularity. This is the supposed point of infinite density where our known laws of physics cease to function. The event horizon is our shield from this realm, the curtain we must understand before we can peek at the secrets hidden inside. But all evidence points to it not being a gate at all. It is a projection, a mirage painted by gravity itself onto the fabric of the cosmos. The firewall paradox. Will you burn or will you float? As you drift toward the immense blackness of a black hole, the universe behind you seems to stretch and fade into a red-tinged memory. The event horizon is crossed, and then there is nothing. No jolt, no flash of light, no cosmic chime to mark your passage. There is only the silent, inexorable fall into darkness. According to general relativity, that is precisely what should happen. Albert Einstein's theory paints the event horizon as nothing more than a spatial illusion, a line on a map that has no physical substance. But in 2012, a group of scientists, including Ahmed Almeri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, dropped a theoretical bombshell that shattered this tranquil picture. The idea they proposed sent shockwaves through the community of theoretical physicists. The event horizon might not be smooth at all, it could be a wall of fire. This is the heart of the firewall paradox. It is a violent clash between three fundamental principles of physics, three ideas that all appear to be true on their own, but cannot peacefully coexist. First, Einstein's general relativity dictates that crossing the event horizon should be an uneventful, smooth experience for an infalling observer. No drama, no instant incineration. Second, quantum mechanics insists that information, the very blueprint of reality, cannot be destroyed. Third, a principle known as the monogamy of entanglement suggests that a quantum particle cannot be perfectly entangled or linked with more than one other system at the same time. When you combine these three seemingly unshakable principles in the context of an evaporating black hole, they collide with the force of a supernova. A black hole emits Hawking radiation in the form of entangled pairs of particles. One particle falls into the black hole while its partner escapes out into the universe. To preserve quantum coherence, the escaping particle must remain entangled with its twin that fell inside. However, to ensure that no information is lost from the universe, that same escaping particle must also be entangled with all the radiation that was emitted earlier. You are breaking a fundamental rule of quantum mechanics. A particle can only be fully married to one other system at a time. Something has to give. The AMPS group proposed a radical solution. At the event horizon, we must abandon the smoothness of spacetime. In their model, the horizon is not a gentle passage, but a high-energy wall of fire that incinerates anything that comes into contact with it. The moment you hit the edge, you are not pulled into the black hole, you burn in place. The picture is shocking. It directly contradicts Einstein's elegant vision of gravity. It does, however, fiercely protect the sanctity of quantum information, a principle many physicists hold even more dear. In the firewall model, information is not lost inside the black hole. It is violently radiated back out in a burst of heat and energy at the boundary. The firewall cuts through the paradox like a cosmic guillotine, making the edge of the black hole a very firm, very final boundary. Many physicists argue that the existence of firewalls is a symptom of our incomplete understanding rather than a true physical solution. They contend that the paradox points to the urgent need for a new, deeper theory of quantum gravity, one that can fully unite the worlds of Einstein and quantum mechanics. Others propose even more exotic alternatives. For instance, the fuzzball theory, which emerges from the complex world of string theory, suggests that black holes are not empty voids at all. They are actually tangled balls of fundamental strings, and they possess no event horizon in the traditional sense. In this view, there is no firewall because there is no clean boundary to begin with. The surface of the black hole is simply a chaotic, fuzzy mess of vibrating quantum information. Then there is the ER equals EPR conjecture, a wild and beautiful idea proposed by Leonard Susskind and Juan Maldacena. It posits that any two entangled particles, the EPR pairs, are connected by a microscopic wormhole, what physicists call an Einstein-Rosen bridge, or ER. If this is true, it could explain how information escapes from a black hole without violating quantum rules and without resorting to a fiery demise at the horizon. But this theory is still in its infancy, and its full implications are barely understood. As of now, the debate over firewalls remains one of the most contentious and exciting frontiers in modern physics. It is a battle between the titans Einstein's vision of gravity versus the unyielding laws of the quantum world. There is still no sign of a peace treaty. But even so, this cosmic puzzle has a very human feel to it. The firewall paradox does not just make us question abstract mathematics, it forces us to question our own assumptions about reality. It makes us wonder what would truly happen if you fell into a black hole. Would it be a quiet fall into darkness or a quick, dramatic death right at the edge ergosphere where space itself spins? Think of a whirlwind. Now picture that the substance being spun is not air or water, but the very fabric of space itself. This is the reality around a rotating black hole known as a Kerr black hole, named after the New Zealand mathematician Roy Kerr, who in 1963 found the solution to Einstein's equations for spinning singularities. In early physics thought experiments, black holes were often simplified as simple, static, non-rotating objects. But in the real universe, most collapsed stars and galactic cores would have some angular momentum, meaning black holes probably rotate. When they do, the fabric of space-time around them is transformed in a truly remarkable way. The ergosphere is a region of space located just outside the event horizon where the warping of space-time is so extreme that nothing can stay still, not even light. If you were to enter this region and try to remain stationary relative to the distant stars, the spinning black hole would drag you along with it. Time and space are being spun like cotton candy in a machine. The pull you feel is not just gravity pulling you inward, it is the current of space-time itself pulling you sideways. This effect is known as frame dragging. It is not just a theoretical concept. Satellites like Gravity Probe B have confirmed this effect, albeit in a minuscule way around our own spinning Earth. But near a spinning black hole, the effect becomes infinitely more powerful. The ergosphere is shaped like a flattened football or an oblate spheroid. It bulges outward at the black hole's equator, a consequence of the centrifugal force of its spin. Unlike the region inside the event horizon, you can technically still escape from the ergosphere, but it would require an enormous amount of energy to fight against the current of spacetime. The ergosphere possesses some strange properties that make it a place where physics bends so hard that it can snap back with a release of energy. This is where things get truly wild. This brings us to the Penrose process, one of the most imaginative ideas in black hole science proposed by the brilliant mathematician Roger Penrose in 1969. This theoretical mechanism suggests that it is possible to extract energy from a rotating black hole by using the ergosphere as a kind of cosmic slingshot. Imagine sending a probe or a spaceship into the ergosphere. Just before it gets swallowed by the event horizon, the craft jettisons a piece of its mass, dropping it into the black hole while the main craft escapes. Here is the twist. Due to the bizarre way space-time is warped, the part that falls in can be arranged to have negative energy from the black hole's point of view. As a result, the escaping part of the ship actually carries away more energy than the entire ship had initially. In essence, the black hole slows its spin by an infinitesimal amount, and you get to ride away with a cosmic energy bonus. Some scientists believe that the spectacular jets of plasma that shoot out from the centers of active galaxies may be powered by a version of this very process. These jets are some of the most powerful phenomena in the universe, capable of stretching for millions of light years into intergalactic space. Many astronomers believe they are driven by twisted magnetic fields in the ergosphere that accelerate charged particles and fling them into space like a cosmic railgun. We are talking about energies millions of times greater than anything the Large Hadron Collider could ever produce. The ergosphere is not just about power, though. It is also about perception. The paths of light, the flow of time, and the very notion of cause and effect behave differently here. Light trajectories follow strange curved paths. If you tried to shine a laser in a straight line, it would be bent into a spiral. It is even possible for objects to appear to revolve backward in time relative to a distant observer. You might even be able to witness events in a bizarre, scrambled order, seeing the end of a process before you see its beginning. Let us talk about the spin itself. A black hole's spin is described by a parameter, a number between 0 for no spin and 1 for maximum possible spin. It is likely that most real black holes fall somewhere in the middle, but some might spin dangerously close to this theoretical speed limit. As that number approaches 1, the ergosphere becomes larger, more energetic, and more twisted. If a black hole was spinning at its maximum rate, the boundary between the ergosphere and the event horizon would become so blurred that the two might almost touch. That would open a gateway into a realm of the most extreme space-time curvature known to physics. The terrifying part is that you would not even feel it at first. If you fell into the ergosphere, you might not notice anything immediately. No blast of energy, no flash of light, but you would slowly, inexorably begin to spin. Not by choice, but by necessity. The ergosphere is a realm where the law is simple, nothing can stay still. You would be caught not just by gravity's pull, but by the turning of the world itself. Your own path would be taken from you, like a leaf caught in a whirlpool. The inside-out black hole hypothesis. What if falling into a black hole does not lead to your destruction, but instead turns you inside out? This is the premise behind one of the most bizarre and speculative ideas in modern theoretical physics, the inside-out black hole hypothesis. It is not a mainstream theory. It has not been rigorously established. But in the minds of theoretical researchers and fringe thinkers, it represents a profound thought experiment that could reshape everything we think we know about the universe and ourselves. The standard story dictates that at the center of a black hole lies a singularity, a point where space-time curvature becomes infinite. It is a place of infinite density and zero volume where the laws of physics break down. But many scientists are deeply uncomfortable with the idea of a true singularity. In physics, an infinity is often a red flag. It is a sign that says, our mathematics has broken down here. There must be something more going on. That something more could be a topological reversal. In simple terms, this means that the interior of a black hole might represent an inversion of the space-time we know, not just in a mirrored sense, but in a deeper structural way. Think of a Mobius strip, a one-sided surface that flips your orientation without you even realizing it. Or consider a Klein bottle, a three-dimensional shape that can be turned inside out without tearing its surface. These are mathematical models of non-orientable surfaces. Some theorists propose that black holes might be the physical equivalent machines that topologically invert space and time. This idea suggests that when matter falls into a black hole, it is not crushed to a single point. It is compressed, yes, it is transformed. But then as it passes through the so-called singularity, it re-expands, not into our universe, but into a mirror domain, a geometric inverse of our cosmos. The interior of the black hole becomes a cosmic negative, where space-time and perhaps even the laws of physics operate in a different or reversed manner. This could help resolve one of the most perplexing problems in general relativity. The equations do not forbid passage through a singularity. They simply become undefined at that point. If you could somehow regularize that point, perhaps by introducing quantum gravity corrections or using higher dimensional topology, you could extend the equations. And what do those extensions show? That the path continues. It continues into a new region, into a new space-time. In some interpretations, this means that every black hole in our universe could be the seed of a new universe. Each black hole gives birth to a new cosmos in its heart, making reality a nested structure like a set of Russian dolls. This idea is sometimes called black hole cosmology. It is purely speculative, but it offers an elegant potential answer to one of the biggest questions of all. Where did our universe come from? In this inside-out model, what was once the center is now the periphery. What was once the periphery is now the center. The singularity becomes the beginning of time in a new universe. Our event horizon becomes that new universe's Big Bang. The interior of the black hole becomes a region of space-time that is contracting, collapsing inward. This is analogous to how our own universe is expanding outward from the Big Bang. The inversion applies not just to location, but to trajectory, to entropy, to causality itself. Now imagine for a moment that you are the one falling into such a black hole. As you pass the event horizon, your perception of space warps, your sense of time begins to twist. You feel the crushing tidal forces, but you are not annihilated. And then, as you approach the center, something else happens. You flip. Like stepping through a looking glass, your trajectory in time continues, but the arrow of space reverses. From your point of view, you are still falling. But in the new inverted universe, you have just been born. You are now expanding outward from what the new inhabitants might call their singularity. You are no longer part of the old universe. You are part of the new. If black holes do give birth to new universes, is our own universe just the interior of such a collapse? Are the laws of physics we observe merely the imprint of a dying star in a larger reality? And can any of this ever be tested? The answer is most likely no. These theories exist at the very edge of observability. The event horizon prevents any probe from returning. The inverted geometry prevents any information from escaping. But sometimes mathematics can see what light cannot. And what it sees is not destruction but transformation. Frozen stars, what distant observers really see. For all the talk of event horizons, spaghettification, and infinite gravity wells, the reality for an observer watching from a safe distance in space is far stranger. According to the mathematics of Einstein's theory of relativity, it appears as though nothing ever truly falls into a black hole. Not really, not all the way. Instead, matter seems to freeze at the very edge, suspended in a state of perpetual motionless descent. This bizarre illusion is the result of a phenomenon known as gravitational time dilation. Time moves more slowly in regions of stronger gravity compared to regions of weaker gravity. Near the event horizon of a black hole, the point of no return, the gravitational pull is so immense that time from an outside perspective appears to slow to a complete stop. Let us imagine an astronaut, a brave pilot, falling into a black hole. As they get closer and closer to the event horizon, the signals they send back to you, light radio waves, anything, take longer and longer to climb out of the gravitational well and reach your distant telescope. Each second of their fall is stretched into minutes, then hours, then days. Their heartbeat, their words, their final wave goodbye would all be slowed, redshifted, and smeared across time. Eventually they appear to stop. There they are, hovering just above the event horizon, but never quite crossing it. Yes, they fade. They grow dimmer. Their light becomes more and more redshifted until it falls completely out of the visible spectrum and into radio waves. But they never technically disappear. From your point of view, they are forever falling but never arriving. Even 1 billion years from now, the very last photon from their descent would still be slowly making its way toward your detector, as if it were struggling through cosmic molasses. This is where the old term frozen star originated. When a massive star collapses to form a black hole, a distant observer does not see the black hole itself form in an instant. Instead, they see the ghost of the matter that fell to create it. They see a shell of the original star frozen in time at the point of no return. However, this story is entirely dependent on the observer. For the falling astronaut, everything feels perfectly normal. They pass through the event horizon without fanfare, without fireworks. They might not even realize they have crossed the line because locally physics behaves as it always has. No sudden wall, no fiery barrier, just a continued freefall into a deepening abyss. This discrepancy between the outside view and the inside experience is one of the strangest consequences of relativity. It is not just a philosophical puzzle. It represents a causal split, a division between two completely different realities. It gets stranger because the same effect that creates this freezing appearance also has profound consequences for light and radiation. Gravitational redshift means that photons emitted from just above the event horizon lose almost all of their energy as they climb away. That is the fundamental reason black holes appear black. It is not because there is a black surface at the edge. It is because any light that tries to escape from that region loses its energy on the way out. It is as if the black hole consumes the energy of light before it can reach you, but we might still be able to see the ghost of what was. Collapsing stars, infalling matter, even entire gas clouds can leave behind faint imprints just outside the horizon. These imprints are like gravitational holograms perpetually visible just outside the void. Astronomers have long debated what this means for the formation of black holes. If all we ever see is matter approaching the event horizon and slowing to an infinite crawl, then when does the black hole actually form? Can we ever point to a moment in time and say, that's when it became a black hole? The answer depends on your frame of reference. For the infalling matter itself, the black hole forms in finite time. The matter is crushed by gravity. For you, the distant observer, the process is one that never truly finishes. The horizon never completely seals itself off. It only approaches that state. From your perspective, the birth of the black hole is an event that will never happen. This is one of the reasons some physicists are skeptical of event horizons altogether. What if they never truly form? What if the black hole is a perpetually forming illusion, always approaching a singularity, but never quite reaching it from our point of view? This leads to alternative models like the firewall or fuzzball, models which attempt to reconcile quantum mechanics and general relativity by eliminating or modifying the standard event horizon. In these models, the frozen star is not a ghost. It is a quantum froth, a wall of fire, or a tangle of strings that behaves very much like a black hole but without the paradoxical features. From a practical standpoint, however, the frozen star effect holds true. Every black hole we have ever observed, from stellar mass remnants to the supermassive giants at the centers of galaxies, behaves as if it has an event horizon. It has a boundary beyond which no echo returns. And everything we know about light curves, radiation patterns, and the behavior of accretion disks is a frighteningly perfect match for Einstein's predictions. Time dilation to infinity. Here on Earth, time feels like a constant, a steady metronome that marches the universe forward. But near a black hole, time does not just bend. It stretches, twists, and ultimately breaks. As you fall toward a black hole's event horizon, you are not just journeying through space. You are journeying through a region of extreme space-time curvature, a gravitational well that alters not only your path, but the very flow of time around you. As you approach the horizon, time from a distant perspective seems to accelerate. At first, the effect is subtle. Your heartbeat feels normal. Your watch continues to tick. But from the perspective of an outside observer, say a friend watching your descent, your actions appear to slow down. 1 second for you might become 2 for them, then 10, then 1,000. Eventually, your time becomes effectively frozen relative to theirs. This is not a theoretical quirk. It is a direct prediction of Einstein's theory of general relativity. Time dilation occurs anywhere gravity is strong, but nowhere is it more extreme than near the event horizon of a black hole. There, the immense gravitational pull slows down local time so dramatically that from the outside it appears you take an infinite amount of time to fall in. Imagine you wave goodbye as you descend. Your friend will see that wave, but each successive motion of your wrist will appear slower until the wave itself is redshifted into nothingness. From their perspective, you simply hang there, your motion so slow it looks like a static image. But from your perspective, time continues to pass as normal. You would feel yourself moving at a normal rate, accelerating faster and faster as you approached the event horizon. Crossing it, you would notice nothing unusual because locally the laws of physics do not stop at the edge. Not for you. But space-time outside is now on fast forward. The moment you cross the event horizon, the external universe begins to speed up from your point of view. In your final moments, as you fall toward the singularity, you could witness galaxies evolve, stars die, and entire civilizations rise and fall. Light from billions of years of cosmic evolution would rush toward you in a single brilliant crescendo. The black hole has become a time machine, but not one that transports you to the past or future. Instead, it allows you to witness the entire future of the universe unfold in an instant. This is not science fiction. It is a direct consequence of the structure of space-time. The deeper you fall, the faster the universe outside appears to move. By the time you are nearing the singularity, the rest of the cosmos may have already experienced its heat death, a state where every star has burned out and every atom has dissolved into cold background radiation. And yet for you, it has only been a few minutes. This concept, infinite time dilation, forces us to rethink what death even means inside a black hole. For most physical processes, the end is a clear boundary. But here it is a gradient, a blur, a passage through which your personal time becomes disconnected from the timeline of the rest of existence. This raises one of the strangest possible questions in modern physics. What if an observer falling into a black hole could witness the end of the universe? Some theories suggest that yes, the infalling observer could experience everything that will ever happen in the universe, whether it ends in a big freeze, a big rip, or even a phase transition collapse. But would they be able to comprehend it or even process it? That depends on the resilience of their consciousness to the extreme tidal forces and gravitational stresses at play. But in principle, physics does not forbid a falling observer from witnessing the future. If black holes evaporate due to Hawking radiation, then a falling observer might never even reach the singularity. From the outside, the process of evaporation takes trillions upon trillions of years. And if the black hole evaporates before you cross the horizon, at least from the outside observer's perspective, your fall was never completed. Did you ever truly fall into the black hole? Or did reality play one last trick on you, leaving you stranded on the edge, trapped between gravity and the clock? Nowhere else in the universe is time accelerated to this degree. That is why black holes are more than just objects. They are portals to a future you can never return from. And they are places where your sense of time becomes utterly disconnected from the universe that made you. The singularity is not a point. In mathematics, the word singularity is a placeholder. In the context of Einstein's equations, it signifies a place where something strange is happening at the center of a black hole. But in physics, an infinity usually just means we do not know what is going on here. It does not necessarily mean there is a real physical point of zero volume and infinite mass. The truth is likely far more complex, and perhaps even stranger. Emerging ideas in quantum gravity and string theory suggest that the singularity may not be a single point at all, but rather a tangled ball of energy loops or buzzing strings. In models like Loop, quantum gravity spacetime itself is quantized, meaning it is composed of incredibly small, discrete units. When enough of these units are crushed together under extreme gravity, they might form a region of maximum density with a finite size, thus avoiding a true infinity. Imagine that instead of falling into a sharp spike, you are falling into a dense fog. It is a place where classical physics breaks down, but where structure still exists. This is the singularity reimagined as a fuzzball, a term that originated in string theory. In this view, the interior of the black hole is not empty space, but a cloud of knotted strings that encode all the information and mass it has consumed. This fuzzball concept directly addresses one of the greatest paradoxes in physics: what happens to information that falls into a black hole. If the singularity is a literal point, and everything that enters is destroyed in it, then information seems to be lost forever, which violates the fundamental principle of quantum mechanics that information must be conserved. But if the core is a fuzzball, or some other kind of structured quantum state, then perhaps the information is stored, albeit in a wildly scrambled and inaccessible way. Some quantum bounce models suggest that quantum processes might eventually halt the collapse of matter inside a black hole. Instead of a singularity, you get a rebound. This means that the matter bounces into a new state or even a new region of space-time. This connects to the fascinating idea that black holes might be gateways to other universes or might give birth to new ones. The singularity is less a destination and more a portal. In this context, it is also important to remember that general relativity, the theory we use to describe black holes, is famously incompatible with quantum mechanics. The singularity is the place where these two great theories meet and fail. Until we have a complete theory of quantum gravity, we will not know for sure what happens in that ultra-dense core. It is a hole in our understanding of physics, a place we know exists but cannot yet explain. The only way we have come close to understanding it is by studying the mathematics of its failure. The equations of general relativity offer nothing to stop the gravitational collapse of a star once it passes the Schwarzschild radius. But those models break down at Planck scale densities, the point where the curvature of spacetime becomes smaller than the smallest known unit of space. That is the point where classical physics ends and the quantum realm must take over. Even some mainstream cosmologists believe the singularity is not a physical point but a limit of our current knowledge. Think of how ancient maps labelled unexplored regions as "here be dragons." The singularity is our modern dragon, the boundary where our maps stop being reliable. What would you see if you were able to survive the fall and witness the core of a black hole? Would you see the blinding white light of compressed radiation, a swirling storm of pure energy, perhaps nothing at all, just a silent darkness, since light itself would not behave as it does in normal space? The scariest part is this: if the singularity is not a point but a dynamic quantum system with memory and structure, then every black hole could be an archive of the universe's most violent events. Every star it consumed, every planet it shattered, and every bit of matter and energy it absorbed could still be there in some form. Black hole holography. Is the universe a shadow? Imagine standing before a vast, featureless wall as black as pitch and as thin as a sheet of paper, yet somehow containing the entire story of everything that happened behind it. Every atom, every star, every falling body. That is the essence of black hole holography. It is one of the most profound and revolutionary ideas in modern physics. It suggests that everything that happens inside a black hole, and perhaps even in the entire universe, could be fully described by information stored on a two-dimensional surface. In a conventional hologram, a flat piece of film creates the illusion of three-dimensional depth. In the same way, our universe could be a three-dimensional projection of information written on a boundary we can never touch. The black hole information paradox, as we have discussed, presented a crisis. Either information was being destroyed inside black holes, violating the sacred rules of quantum mechanics, or there had to be a way for that information to escape or remain encoded. The solution proposed by theoretical physicists Gerard 't Hooft and later Leonard Susskind was wildly imaginative. What if black holes do not store information on the inside, but on their surface? This idea became known as the holographic principle, and it states that the universe stores information not in volumes, but on surfaces, specifically the surfaces that enclose those volumes. For black holes, this means that the event horizon, the invisible boundary beyond which light cannot escape, becomes a kind of cosmic ledger, a two-dimensional surface that keeps a record of everything that falls into the darkness. The implications rocked the world of physics. The old picture of black holes as empty voids was quickly replaced by the idea that their exteriors might be far busier and more complex than their interiors. This shift was reflected in Stephen Hawking's own later work. Instead of erasing information, black holes might store it on their horizons, encoded in microscopic degrees of freedom, tiny variations in the fabric of spacetime that we are only just beginning to comprehend. This theory gained enormous traction with the development of the ADS divided by CFT correspondence. a mathematical bridge built by physicist Juan Maldacena in the late 1990s. He demonstrated that a type of gravity-based theory in a higher dimensional space called anti-de Sitter space could be mathematically equivalent to a quantum field theory on its lower dimensional boundary. In plain terms, the physics inside the volume matched the physics on its surface. It was a perfect testbed for holography. Although our real universe is not shaped like ad space, the success of this mathematical model gave physicists hope that something similar might apply to our own cosmos, or at least to black holes. What does this mean in practical terms, though? When you observe a black hole, you see its mass, its spin, and its immense gravitational field. If holography is real, all of that is just a manifestation of quantum information written on its event horizon. The interior might not even exist in the conventional sense. It could be a convenient illusion, a projected volume that emerges from a two-dimensional description. So falling into a black hole might not be like falling into a deep well, but more like merging with a cosmic library written on the boundary of space and time. It is like watching a three-dimensional movie. The story you see on screen is just an illusion created by light projected from a flat panel, but the characters and scenery appear real. According to holography, our universe might be pulling off the same trick on a cosmic scale, and not just in black holes. In fact, black hole holography might offer insights into one of the most elusive goals in science, unifying general relativity, Einstein's theory of gravity, and the large with quantum mechanics, the theory of the very small. So far, they have refused to play nicely together. But holography, by bridging quantum information with gravitational surfaces, might be the Rosetta Stone we have been waiting for. If information is stored on a black hole's horizon, it must be incredibly compressed. We are talking about a staggering data density. According to the Bekenstein-Hawking entropy formula, the amount of information a black hole can hold is proportional not to its volume, but to the area of its event horizon. This flips everything we know about storage on its head. A single Planck-sized area on the event horizon could hold 1 bit of information. This means there might be more information contained in a tiny region of a black hole's surface than your brain could ever process. If that does not make you shiver, this might, in this model, you, your atoms, your thoughts, and your memories might also be projections of information stored on a distant space-time boundary. You are not just in space and time, you are a projection of it. This does not mean our experiences are not real, but it could mean that reality is built on a fundamentally different set of rules than we assume. Black holes, once thought to be agents of destruction, may be the key to understanding that deeper structure. Gravitational lensing inside a black hole. Gravitational lensing is one of the most beautiful and visually stunning consequences of general relativity. It distorts the paths of light, reshapes the appearance of the cosmos, and allows us to peer into the distant past. In our universe, lensing occurs when light from a distant galaxy or star passes close to a massive object, like another galaxy or a black hole. This bends the light's path, creating arcs, rings, or even multiple images of the same object. But what does this phenomenon look like from inside a black hole? Once you pass the event horizon, the escape velocity exceeds the speed of light. Can light still bend in ways that allow you to see what is behind you, or even more terrifyingly, to see yourself? Outside a black hole, gravitational lensing is a well-understood phenomenon. It is a funhouse mirror made of space-time. But inside the event horizon, the rules of physics are radically different. Here, space and time effectively switch roles. Radial distance becomes a time-like dimension, and time becomes more like space. It is hard enough to picture this inversion on its own, but now add light to the mix. Inside the black hole, light is still trying to travel along the straightest possible paths, what physicists call null geodesics. But in this bizarre geometry, those geodesics curve, twist, and loop in unpredictable ways. The gravitational field is not just strong, it is all-consuming, forcing even the most stubborn photon into a chaotic ballet. And now for the crazy part. The curvature of space-time is so extreme that a beam of light could in theory circle the interior of the black hole multiple times before reaching your eye. This opens up the strange and eerie possibility of visual recursion. This means you could potentially see an image of the back of your own head shortly after falling in. Not a reflection, but a time-delayed image of your own past. You are not looking in a mirror. You are looking at a causal loop, a gravitational echo of your own journey. This is gravitational lensing turned inward on itself. It gets even stranger in the case of spinning black holes or Kerr black holes. As we have discussed, a spinning black hole drags space-time around with it in a process known as frame dragging. Outside the event horizon, this swirling region creates the ergosphere, but its effects extend to the interior as well. Inside, photons can become trapped in these swirling vortices of light orbiting in circles that never quite settle. The more angular momentum the black hole has, the more chaotic and tangled the light paths become. Space and time do not just bend, they spin. Mathematical studies of these trajectories have identified the potential for closed, null curves paths, where light travels in a loop that returns to its starting point in both space and time. This is more than just seeing your own back. This is potentially seeing your own past unfold before you, distorted and folded by the forces of gravity and motion. Light that loops in this way might allow a hypothetical observer to see events happening outside the black hole, even after they have crossed the event horizon. Some theories suggest that a tiny fraction of distorted starlight could still find its way to the traveler's eyes, offering a warped and fading glimpse of the universe they left behind. It would be a final goodbye, one bent and stretched by the cruel laws of gravity. Now, combine this with the photon sphere, a theoretical region where light orbits the black hole. Outside the event horizon, photons in this sphere are on a knife's edge, destined to either fly off or fall in. Inside, no one really knows. The models suggest that trapped light could swirl in bizarre patterns, creating multiple flickering images of everything falling in. You might witness the last screams of infalling matter, see the ghosts of other objects spiraling toward the singularity, and even see your own limbs stretching into nothingness over and over again. Inside a black hole, gravitational lensing would be not just disorienting but terrifying. Your visual field could become a sphere of flashing images. These images would be time-delayed by relativistic effects, distorted by curvature, and layered on top of each other like a kaleidoscope of doom. There would be no darkness. There would be an overwhelming sensory overload. Light from all directions, some from moments ago, some from hours ago, all converging on you as you descend deeper into the most twisted region of space-time. In this case, the black hole is less of a void and more of a lens of eternal memory, one that records, distorts, and plays back the final moments of everything it consumes. And if you could somehow escape, you might carry with you the ultimate visual record of the universe's fall. Matter gets spaghettified, but what happens to consciousness? The term may sound like something that happens when you leave pasta in boiling water for too long. But in the terrifying lexicon of astrophysics, spaghettification describes one of the most extreme and violent phenomena that can occur in the vicinity of a black hole. Tidal forces stretch matter into long, thin filaments capable of tearing apart atoms, bones, and even the fabric of molecules. But while we understand the physical fate of matter, a much stranger question lies just beneath the surface. What happens to your consciousness as you fall in? Let us start with the physics. Tidal forces are the result of gravitational gradients, differences in the pull of gravity on different parts of an object. Near a small or stellar mass black hole, this gradient becomes so intense that your feet would experience vastly more gravity than your head, stretching your body into a filament of atomic thread. The closer you fall, the more extreme the gradient becomes. At a certain point, molecular bonds snap. Even protons themselves may not survive. This is the domain of physics, where bodies and matter dissolve into cosmic dust. But what about the mind? If consciousness arises from the brain, a 3-pound organ governed by electrochemical signals, then is it simply obliterated as the brain is torn apart? Does your final moment of awareness coincide with the moment your nervous system fails? According to Einstein's general relativity, an observer falling into a supermassive black hole like the one at the center of a galaxy might not experience anything dramatic at the event horizon. The gravitational gradient could be gentle enough to allow a person to cross the threshold without immediate destruction. In that case, spaghettification might not occur until much later, granting consciousness more time to observe the descent. How would that feel? Imagine that from your perspective, time begins to distort. The universe outside the black hole appears to accelerate rapidly. Stars swirl, galaxies evolve, and perhaps even civilizations rise and fall in a blur. But not you. You are trapped in a bubble of slow motion, your perception thinning along with your physical form. If any awareness remains, it would be like watching the universe on fast forward as you slowly dissolve into nothing. And then comes the final stretch. As spaghettification begins in earnest, your sensory inputs would go haywire. Gravity pulls harder on your feet than your chest, harder on your chest than your head. Nerve signals fail. Your vision becomes distorted as blood flow ceases. Your body, no longer unified, ceases to act as a single system. But the brain, that mysterious lump of grey matter, might still be intact, if only for a few milliseconds. Could those milliseconds contain a lifetime? Some theories suggest the brain could experience a flood of information at the end, similar to the life flashing before your eyes reports from near-death experiences. Trapped in a relativistic cocoon, your final moments might seem eternal from your perspective, an endless descent where time loops and folds in on itself. What if consciousness is not just a biological byproduct? Some speculative models in quantum mechanics, and yes, this is fringe territory, propose that consciousness could be tied to quantum states in the brain. If that were true, a massive if-then entering a region of extreme space-time curvature, like a black hole, might do something very peculiar. It might entangle the brain's final quantum state with the geometry of the black hole itself. These words could mean that a part of your mind is built into the black hole. This is pure speculation, but some physicists argue that since the information of infalling matter cannot be lost, that must include the precise configuration of a brain. We will discuss the black hole information paradox later, but this idea is at its core. If the information of your mind is preserved, etched into the horizon, or warped into Hawking radiation, could some vestige of your consciousness also persist? Or perhaps the spaghettification of matter is also the spaghettification of experience. One final fractured impression of falling, stretching, and fading into nothingness, played over and over again, in an endless time, dilation until awareness dissolves completely, chaos at the core, the butterfly effect in curved space-time. Imagine dropping a feather into a hurricane. Now imagine that hurricane is inside a black hole, a place where space-time itself is violently twisted, compressed, and warped. In such an environment, the slightest change, a particle shifting by a quantum width, could lead to profoundly different outcomes. This is the essence of chaos theory, but amplified to an extreme degree by the intense curvature of space-time. Inside the core of a black hole, the butterfly effect might not just be a metaphor, it might be the defining feature of reality. Chaos theory in its classical form suggests that small changes in initial conditions can produce dramatically different results. It is famously illustrated by the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. But classical chaos assumes a deterministic system, one that, while unpredictable, still follows a specific set of rules. Inside a black hole, however, we are dealing with a system where those rules break down, or at the very least mutate into something stranger. As matter falls toward the singularity, the equations of general relativity tell us it accelerates indefinitely. Time and space twist together, and paths through space-time. What physicists call geodesics can intersect loop or spiral in unpredictable ways. Even the tiniest perturbation, a subatomic fluctuation, a photon's nudge, can send a particle careening down a drastically different path. This is not just theoretical. Mathematical models of rotating Kerr black holes suggest a region called the Cauchy horizon, a point beyond which predictability completely collapses. Past that threshold, determinism fails. Causality becomes a suggestion, not a law. In some black holes, this means that the past may no longer uniquely determine the future. Even our best equations are useless if the outcome is governed by chaos. Furthermore, this loss of predictability could be seen as a strange form of freedom, a mechanism for resetting the fundamental rules of the universe. In these chaotic regions, space-time could fold in on itself, creating time loops, causal paradoxes, or the spontaneous emergence of new structures like baby universes or wormholes. This space-time chaos is amplified by the inherent randomness of quantum mechanics. Virtual particles, the fleeting bursts of matter and energy that pop in and out of existence, could be caught in feedback loops, amplified by gravitational shocks, or trapped in closed time-like curves. The result is a picture of space-time that is constantly in flux, roiling with its own fluctuations. A single atom could trigger the formation of a space-time fissure. A quantum fluctuation could set off a chain reaction of gravitational echoes that propagate in a statistically unpredictable way. It is chaos, but not the kind we are used to. It is a new category, curved space chaos. It is a feedback system that is not just sensitive to initial conditions, but also to the geometry of the space those conditions unfold in. We will now return to the idea of an observer, a person or entity falling into the heart of this maelstrom. What would their experience be? It is highly likely that their perception would be completely scrambled. The concepts of up and down would lose their meaning. The sky, if there was one, might appear to bifurcate and refract. Light could loop back on itself, creating strange mirages or visual echoes of events that have yet to occur. Time could speed up, slow down, or pause without warning. In such a system, consciousness itself, if it still functioned, might lose its connection to linear experience. The implications for information are even more profound. If the core of a black hole is chaotic, how can information be preserved? The butterfly effect in curved spacetime suggests that even small bits of information, like the spin of a particle, could be amplified, scrambled, or even duplicated in different regions. This creates enormous problems for quantum mechanics, which demands that information must be conserved and remain unique. Is it possible that the chaotic heart of a black hole holds the key to resolving the information paradox, or is it a sign that our current theories are fundamentally wrong? Inner horizons, black holes within black holes. Once you pass the event horizon of a rotating black hole, you may find yourself in a region of space-time so strange that even physicists struggle to describe it. For inside this cosmic monster, there may not be just one horizon but two. These are not layers like the crust and core of a planet. They are boundaries in space-time where the rules of physics shift abruptly and dramatically. These are the inner horizons. They are a secret world where black holes might be more like Russian nesting dolls than simple empty pits. In the case of a non-rotating, uncharged black hole, a Schwarzschild black hole, the structure is relatively straightforward. One event horizon, one singularity. But for black holes that rotate, called Kerr black holes or carry an electric charge, Reissner-Nordstrom black holes, the interior geometry becomes radically more complex. Here, physicists predict the existence of multiple horizons, the familiar outer event horizon, and a second mysterious boundary deeper in called the inner horizon or Cauchy horizon. What makes the inner horizon so special and so dangerous is what it represents. While the outer event horizon marks the point beyond which light cannot escape, the inner horizon is a boundary where causality itself can break down. Time and space can flip roles, and the known laws of physics no longer provide reliable predictions. The Cauchy horizon gets its name from the Cauchy problem in mathematics, which determines whether a system's future can be predicted based on its initial data. Cross that line and prediction becomes impossible. The inner horizon is more than just a mathematical curiosity. In models, it acts as a dynamical trap capable of amplifying even the smallest perturbations to infinite levels. From the perspective of an observer falling into the black hole, a single photon, a tiny particle of light, could become infinitely powerful as it crosses the inner horizon. This creates what physicists call a mass inflation singularity, a region where the effective mass of the black hole seems to explode, warping spacetime even more violently. This is the inner horizon acting as an amplifier for cosmic noise, turning whispers into screams. Some solutions to Einstein's field equations suggest that passing through the inner horizon does not always lead to a singularity or the end of the journey. It might instead open up into a different region of space-time or even a different universe. In these scenarios, a black hole could possess a wormhole throat, a narrow passage that leads to a new expanding region. That expanding region might look very much like a Big Bang. This implies that black holes might not be the end of the universe, but the beginning of a whole new one. So it is possible that every black hole contains its own universe, complete with its own space, time, and perhaps even its own physical laws. Even more bizarrely, that new universe could contain its own black holes. And inside those even more universes, this leads to the idea of fractal cosmology, the theory that the multiverse might be composed of black holes within black holes, each one giving birth to its own cosmos. If this is true, our own universe might be inside a black hole in a parent universe we can never see. The Big Bang, nothing more than a rebound from a stellar collapse beyond another horizon. So the inner horizon could be the key to connecting different universes, turning black holes from points of no return into gateways of infinite possibility. There is a catch, though. For all their elegance, these scenarios come with significant potential pitfalls. The extreme conditions near the inner horizon mean that even tiny quantum effects could have a massive impact on the outcome. Some physicists argue that quantum gravity, which we do not yet fully understand, would likely fuzz out or eliminate the horizon altogether. Others believe that quantum effects would make these tunnels unstable, causing them to collapse before anything useful could pass through. The inner horizon is so finely balanced between stability and instability that any attempt to cross it effectively destroys it, and yet the hints remain. The structure of rotating black holes, the peculiar mathematics of Einstein's equations, and even some speculative models from string theory all leave the door open for inner horizons and for the bizarre possibilities they contain. If we could ever observe gravitational waves or radiation signatures from within a black hole, a currently impossible feat, we might someday find evidence of this inner landscape. Closed time-like curves. Can you time travel inside? The ability to travel back in time does not have to be the stuff of science fiction. In the warped reality of a spinning black hole, it could be a feature built into space-time itself. Closed time-like curves, or CTCs, are bizarre space-time trajectories that loop back on themselves, allowing an object to return to its own past. This is speculative, of course, but not impossible. The math is not so clear. These strange loops appear naturally in some solutions to Einstein's equations of general relativity. This is especially true for rotating Kerr black holes. Time-like curves describe the possible paths that a massive object like a person or a spaceship could take through space-time. A closed time-like curve means that the object returns to the same point in space and time from which it began. That is time travel, even if the space-time it travels through is incredibly strange and distorted. This is how it would work in principle. A Kerr black hole has such extreme gravity and spin that it warps space-time so profoundly that time does not just slow down, it loops back on itself. The effect is known as frame dragging, and it means that space-time is being dragged around the black hole like taffy around a spinning stick. In the ergosphere, a region just outside the event horizon, this effect is so strong that all objects are forced to move in the direction of the spin. But deeper inside, past the inner horizon, the equations allow for paths that loop backward as well as forward in time. This idea is not new. In 1949, the logician Kurt Gödel, the same Gödel of the incompleteness theorems, found a solution to Einstein's equations that described a rotating universe filled with CTCs. His model was not physically realistic, as it required a rotating universe filled with exotic matter, but it demonstrated a crucial point. General relativity under the right conditions allows for time travel. Kerr black holes became the most tantalizing candidates for such a phenomenon. The combination of spin and gravity might wrench space-time open to allow such loops, at least mathematically. Some physicists suggest that entering a CTC could mean visiting your own past, encountering earlier versions of yourself, or in the most extreme version, creating paradoxes. This is the so-called grandfather paradox, where a traveler could interfere with their own origin. But the universe does not like paradoxes. That is where the speculation gets divided into two camps. One believes the laws of physics would prevent these curves from ever forming, in reality through a mechanism like quantum back reaction or chronology protection, as Stephen Hawking proposed, while the other believes nature might allow it but hide it well. For a closed, time-like curve to exist inside a black hole, the interior would have to be not just weird but stable. And there is the catch. Most theoretical studies show that even the smallest disturbances near these curves could cause infinite feedback loops of energy, destroying the very conditions that allow the loop to form. In other words, any attempt to use the time loop breaks it. Physicists have found clever ways to model CTCs using concepts from quantum mechanics and general relativity. Some researchers have tried building simplified versions of time machines using wormholes stabilized by exotic matter material with negative energy density. Others have explored quantum models that avoid paradoxes by invoking many worlds interpretations. Every trip back in time spawns a new timeline, avoiding direct contradictions. Even with all this mathematics, no physical evidence exists that CTCs are real. We have not observed anything, no particles, no fields, that behaves as though it is moving backward in time. Nor have we found black holes stable enough, observable enough, or close enough to even consider testing the hypothesis. But that does not make it any less interesting. If time loops are real, they have implications that go beyond science fiction. They suggest that black holes are not just one-way trips into nothingness. They are complex dynamic systems with internal structures that could connect different points in space and time. That could change how we think about chaos, causality, and even the creation of universes. Could black holes humming quietly in the void be the universe's built-in time machines, looping bits of existence inside them like old film reels? Or are these structures just mathematical phantoms forbidden from existing in the real world? Naked singularities, cosmic censorship breaking down. Black holes are supposed to keep their secrets. This assumption is the basis for another of physics' most terrifying questions. What if they do not? Imagine that the singularity, the terrifying core of a black hole, was not shielded by an event horizon but was instead exposed to the rest of the universe. This is the chilling concept of a naked singularity, a place where the laws of physics break down in plain sight, where gravity's failure is visible to all. If such an object existed, it would violate one of the most fundamental assumptions about the way the universe works. The traditional black hole, as described by general relativity, contains a singularity at its center. It is a point, or more likely, a region where matter is crushed into infinite density and space-time curvature becomes extreme. But in a normal black hole, that singularity is safely hidden behind the event horizon. Once something crosses that boundary, it can never return, and more importantly, it can never send information back out. This protective veil is what keeps the rest of the universe safe, from the singularity's chaos. This idea is formalized in the cosmic censorship hypothesis proposed by Roger Penrose. It posits that nature censors singularities by always enclosing them behind horizons. According to this conjecture, no observer in the universe should ever see the singularity directly. It is like a firewall that preserves the laws of physics by preventing the breakdown from spilling into our reality. But what happens if this censorship fails? In certain scenarios, like the collapse of specific kinds of matter or the interaction of exotic objects like rapidly spinning black holes, it is theoretically possible for naked singularities to form. In a Kerr black hole, if the spin exceeds a certain limit, the mathematics suggests that the event horizon could vanish, leaving the singularity exposed. That would be like removing the containment shell of a nuclear reactor while it is still running. If naked singularities exist, they would be the ultimate physical anomalies. They would be places where our predictive models fail, where determinism breaks down, and where cause and effect might lose their meaning. Because a naked singularity is observable, light, or any other form of information could theoretically escape from it. This would mean that the chaotic and unpredictable physics near the singularity would influence the rest of the universe. The result could be a breakdown in everything from the laws of thermodynamics to the arrow of time itself. These bizarre possibilities are not just abstract mathematics. Some numerical simulations in general relativity, especially those involving asymmetrical or high-energy collapses, have shown hints that naked singularities might form under extreme conditions. One such case involves the collapse of a scalar field in spherical symmetry. While most simulations still respect cosmic censorship, there are edge cases that flirt with exposure. The ideas of quantum gravity from string theory and loop quantum gravity complicate the picture further. Some argue that when quantum effects are taken into account, the classical notion of a singularity disappears entirely. However, this does not mean that something incredibly strange could not still be visible where an event horizon once was. In string theory, for example, singularities could be replaced by fuzzballs, dense collections of brains that in some scenarios could be naked. Then there is the observational perspective. Although we have never directly observed a naked singularity, some astrophysicists speculate that strange high-energy events like certain gamma-ray bursts or ultra-luminous X-ray sources could be signatures of them. These strange events are far from proof, but they do raise tantalizing questions. Are we sure we have not already seen something we cannot explain? If a naked singularity were ever proven to exist, it would force a complete rethinking of general relativity and everything we assume about space-time. It could even lead to new physics, new particles, or new dimensions we do not yet know about. It might also help solve some of the universe's biggest mysteries, like the origin of dark energy or the beginning of the universe. But the implications are deeply unsettling. A visible singularity could emit unpredictable radiation, violate physical laws, or trigger feedback loops that destabilize entire regions of space. At times, it might even behave like a glitch in the matrix, a tear in the fabric of reality. This is why many physicists still believe in cosmic censorship, trusting that nature always hides her singularities. The black hole heartbeat. At first glance, black holes seem like the quietest, most static objects in the universe. They are eternal black voids, engaged in a slow, relentless process of consumption. But astronomers have discovered something strange pulsing in the darkness, flashes, flickers, and bizarre rhythms emanating from the very edge of the abyss. They are not random. They appear to be clocked. They repeat. It seems that in some cases black holes have hearts. The phenomenon is known as quasi-periodic oscillations, or QPOs, and it is one of the strangest behaviors ever observed around black holes. QPOs are regular flashes of X-ray light seen coming from the accretion disks of some black holes. These are the whirling vortices of gas and dust that are hurtling toward destruction. These flickers occur at precise intervals, sometimes hundreds of times per second, other times only once every few seconds. They always maintain a consistent frequency, which suggests that something highly organized is happening very close to the event horizon. It is hard to believe that a black hole can pulse. These heartbeats are not caused by the black hole itself twitching like a muscle. Instead, they arise from the complex interplay of matter in the accretion disk as it is accelerated by extreme gravity. Some scientists say that the regularity of the light produced by these oscillations is so striking that it is analogous to seismic waves from a planet's core, or even the rhythm of a heartbeat. This is a strange comparison given that black holes are the dead remnants of collapsed stars. One remarkable example was discovered in the black hole system, IGRJ 1709-13624. It displayed heartbeat-like rhythms that were so regular they mirrored those seen in GRS 1915 plus 105, a larger, more well-known black hole system. The mechanism is thought to be a limit cycle instability, a process where matter builds up in the inner accretion disk, becomes intensely hot and brightens up. It then cools and dissipates, and the cycle begins again. It is like a cosmic clock. These heartbeat rhythms are more than just a poetic headline. They contain crucial information about the geometry and behavior of space-time close to the event horizon. The frequency of the oscillations can be linked to the black hole's mass and spin, as well as to relativistic effects like frame dragging, the twisting of space-time by a spinning massive object. Heartbeat black holes may be showing us the finer points of general relativity in action. Some models suggest that these QPOs are created by hotspots, orbiting just outside the innermost stable circular orbit, or ISCO. This is the last safe zone for matter before it plunges into spacetime. These hotspots could be regions of magnetic turbulence or density spikes. Their orbital motion modulates the light we receive like a lighthouse signal. The result is a periodic brightening and dimming of light that is closely tied to the dynamics of these inner disk regions. Magnetohydrodynamic oscillations are another potential explanation. These are waves of plasma that are driven by magnetic fields in the accretion disk. When these magnetic effects are amplified by strong gravity, they may create standing waves that propagate across the disk like drumbeats. In this case, black holes are not just crushing matter, they are also orchestrating a symphony of plasma and light. It is also possible that QPOs are signatures of precession, a wobbling motion in the center of the accretion disk caused by frame dragging. This would mean that we are seeing the disk tilt back and forth over and over again like a coin slowly losing its balance as it spins. The regularity of this motion would show up in the light curve as periodic bursts from our perspective on Earth. Whatever the cause, the consistency and power of these signals have astounded astrophysicists. The stability of these rhythms is so remarkable that some have proposed using QPOs as cosmic clocks. This could help us measure cosmological distances or test fundamental laws of nature. In the distant future, they could even serve as navigational beacons for interstellar travel, guiding ships through the darkness. But beyond the science, there is something hauntingly poetic about a black hole with a heartbeat. These objects are supposed to be death-incarnate points of no return where everything vanishes, and yet here they are pulsing, whispering in X-rays, beating with a rhythm that cuts across light years to reach us. Sound of the singularity. Sound waves cannot travel through the vacuum of space. It needs a medium to propagate through like air, water, or some other substance. In the silent expanse of space, even the most violent cosmic events occur without a sound. Yet, when we delve deep into the physics of black holes with their strange geometries, extreme matter densities, and quantum uncertainties, a fascinating question arises. What would it sound like to fall into a singularity? Could the bending of space-time itself propagate in a way that resembles sound? In their final moments, or in the most extreme environments, black holes might be producing a kind of space-time, music that we are only now learning to hear. In recent years, physicists and astronomers have begun to sonify black hole data. That is, they translate gravitational wave patterns, accretion disk vibrations, or X-ray bursts into audible frequencies. And the results are eerie. The merger of two black holes, for example, creates a gravitational wave pattern that, when sped up and made audible, produces a sound like a chirping whoop, a cosmic bird call that marks the collision of titans. But what about the singularity itself, the very core of the black hole? Could anything escape it, even as a wave, a frequency, a note? We know that the singularity represents a mathematical breakdown, an endpoint where known physics collapses into infinite density and zero volume. But there are theories that suggest this point may not be a point at all. Some suggest it could be a compressed structure, or even a kind of vibrating brain in a higher dimensional space. In string theory, singularities might be replaced by fuzzballs, dense tangled loops of string vibrating in complex pattern. If that is the case, those vibrations would not produce sound in the conventional sense, but they might create resonances in space-time itself. Those resonances could ripple outward. We would not hear them with our ears, but we might detect them with our instruments, gravitational wave detectors, for instance. Think of space-time like a drumhead. When something disturbs it like a massive object collapsing into a singularity, it does not just disappear, it sends out ripples. Those ripples, if converted to frequency space, become tones. Music, in a sense, not music of air, but music of space-time. This is where speculation comes in. For some scientists, like those who work with loop quantum gravity, the singularity is not an end, but a transition, a bounce. In this model, quantum effects create a repulsive force that causes matter to rebound when it collapses to extreme densities. This rebound could, in theory, create a shockwave in spacetime, the singularity's final gasp, before it transforms into something else like a white hole or a baby universe. That shockwave could have a unique frequency signature, one we could detect and convert into music if we knew how to listen. There is another dimension to this puzzle, one that involves psychoacoustics, the study of how potential black hole environments might affect the brain's perception and cognition. Let us say you could survive the journey inside. What would your mind process as the very fabric of space-time dissolved around you? Would you hear the glitches as sounds? Would the slowing of time stretch your final thoughts into a seemingly infinite drone in a purely relativistic sense? The stretching of space could create perceptual waves blending sight, sound, and touch into a single confusing signal. NASA and other institutions have begun turning black hole data into audio, not just for educational outreach, but for pattern recognition. The vibrations of matter in an accretion disk, the frequencies of quasi-periodic oscillations, and even the structure of gravitational lensing can all be translated into tones revealing patterns the eye might miss. The singularity, though still theoretical, could be the ultimate note, a final vibration so deep, so profound, it hums below the fabric of reality. Fuzzball theory, string theory's black hole alternative. When we imagine a black hole, we typically picture an object so dense and so brutal that it crushes all matter into a singularity, an infinitely small point of infinite density. But this picture is not only deeply unsettling, it is also deeply problematic. It defies the laws of quantum mechanics. It contradicts our ideas about the nature of space-time, and it creates paradoxes that have stumped scientists for decades. Fuzzball theory is a bold and elegant proposal from the world of string theory that aims to rewrite the narrative of what a black hole truly is. Instead of a singularity hidden behind a featureless event horizon, fuzzball theory suggests that black holes are tangled, quivering balls of stringy energy, a change that alters everything. Fuzzball theory originates from attempts to solve the infamous black hole information paradox, the idea that anything falling into a black hole is lost forever, violating the laws of quantum mechanics which insist that information must be conserved. According to fuzzball theory, this paradox only exists if we assume the traditional black hole model, an empty space, with all mass compressed into a point at the center. But if instead the interior of the black hole is filled with tangled strings, each carrying specific quantum information, then nothing is truly lost. The black hole's information is not hidden behind an event horizon. It is the fuzzball. So how does this idea work in practice? String theory posits that all fundamental particles are composed of tiny vibrating strings. The different vibrational modes of these strings give rise to different particles, electrons, quarks, photons, and so on. In a region of extreme energy like the collapse of a massive star, these strings can clump together into a vast tangled structure. In the fuzzball picture, this clump replaces both the singularity and the event horizon. The event horizon is not an empty boundary. It is composed of a tangled mass of strings pulsing and vibrating with quantum activity. This changes the nature of the event horizon in a crucial way. According to classical general relativity, the event horizon is a point of no return. It is a passive boundary where nothing unusual happens to an infalling observer. In fuzzball theory, there is no such thing as an empty event horizon. Instead, the surface of the fuzzball is made of stringy matter, and falling into it is not a smooth process. It is like hitting a wall of quantum chaos. Some even compare it to encountering a firewall, an idea that emerged from earlier attempts to solve the information problem. What is remarkable about fuzzball theory is that it offers a potential mechanism for Hawking radiation to carry information. In the standard view, black holes evaporate slowly over trillions of years by emitting Hawking radiation, a process that seems to be random and uninformative. But if black holes are fuzzballs, then their surface made of strings could emit radiation in a way that subtly encodes information about the matter that fell in. Think of it as a complex symphony of particles radiating outward, each one containing a whisper of what came before. But how do we test this? Unfortunately, fuzzball theory exists deep in the domain of high-level string theory, a framework that is notoriously difficult to verify experimentally. Still, it has gained traction among theorists because it offers mathematical consistency and a potential resolution to problems that have stymied physicists for half a century. And while we cannot yet probe the interiors of black holes directly, future observations of Hawking radiation or unexpected features in gravitational wave data could one day provide indirect evidence. The implications of fuzzball theory for the experience of falling in are another interesting consequence. If a black hole is a fuzzy ball, then crossing the event horizon would not be a smooth experience. It would be a violent one. The infalling object would interact with the stringy surface in a way that is very different from the classical freefall into a singularity. It could be torn apart or assimilated. This is a dramatic departure from Einstein's equivalence principle, which states that the event horizon is locally indistinguishable from empty space. Some theorists go even further, suggesting that each black hole fuzzball is unique with a quantum structure that depends on the precise composition of the matter that collapsed to form it. In other words, no two black holes are alike. Each is a cosmic fingerprint of its own history written in the language of strings. Fuzzball theory also inspires philosophical questions. If black holes are essentially collections of pure information, could they behave like computational engines? Could the oscillations of their strings be performing calculations, storing memory, evolving code? It may be far-fetched, but it is not entirely out of line with ideas in theoretical physics today, where the line between information theory and cosmology is increasingly blurred. The Einstein-Rosen bridge shortcut, or death trap. It sounds like something straight out of a science fiction novel, a tunnel through space-time connecting distant parts of the universe, or even two entirely different realities. This idea was first proposed in 1935 by Albert Einstein and his collaborator Nathan Rosen, as they grappled with the strange mathematical implications of general relativity. The result was the Einstein-Rosen bridge, or as it is more popularly known, the wormhole. While this hypothetical tunnel is often romanticized as a galactic subway, the reality is far more complex and potentially lethal. The Einstein-Rosen bridge arises naturally from the equations of general relativity for a non-rotating, uncharged black hole, the so-called Schwarzschild solution. In this solution, space-time not only curves inward but also folds back on itself, creating a bridge between two identical back-to-back black holes. On paper, it looks like a tube connecting two sheets of space-time. One side is our universe, or at least a region of it. The other side, it could be another universe, a mirror image of ours, or a distant part of reality that bears no resemblance to home. There is in fact a problem before you pack your bags for the Galaxy Express. First, the Einstein-Rosen bridge is inherently unstable. The moment any massive object, even a single photon, attempts to pass through it, the tunnel collapses. It would be like trying to walk across a bridge made of paper. The instant you apply weight, it rips apart. The collapse is so rapid that not even light could make it to the other side before the tunnel pinches off. That has not stopped physicists from exploring ways to stabilize a wormhole. One idea involves something called exotic matter, a hypothetical substance with negative energy density. Negative energy is not just sci-fi gobbledygook. It is a real concept in quantum field theory, albeit one we have only observed in incredibly limited laboratory-scale phenomena like the Casimir effect. If enough exotic matter could be placed around the mouth of the wormhole, it might prop it open long enough for travel. But finding or generating this material on cosmic scales, that remains firmly in the realm of theoretical speculation. Even if you could somehow stabilize a wormhole, the journey would not be like taking a leisurely walk through a cosmic hallway. The tidal forces near the mouths of wormholes, regions of extreme gravitational curvature, could easily stretch and crush any traveler into oblivion. These distortions are closely related to the spaghettification effect found near black holes, where gravity pulls harder on one end of an object than the other. For now, it seems any trip through an Einstein-Rosen bridge would be one way and one life only. Beyond this apparent contradiction lies a greater problem, the issue of causality. If wormholes are traversable, they open the door to faster-than-light travel, and even time travel. Imagine exiting the portal before you entered it. In the grandfather paradox, you could prevent your own birth, leading to a host of other contradictions. Violating causality in this way is anathema to physics, particularly relativity. This is one reason why many scientists believe that even if wormholes exist, they are constrained in ways that prevent them from violating causality. This might be due to quantum gravity effects. The concept has not died. In recent decades, theorists like Kip Thorne and Michael Morris have explored traversable wormholes in more advanced models of spacetime that include rotation, electric charge, or extra dimensions. Some solutions suggest that if a wormhole connects two regions of an accelerating universe like our own, the distance might be short enough on a quantum level to permit a form of limited communication or interaction. Then there is the tantalizing idea from string theory and quantum gravity that wormholes might be more than shortcuts. They could be the very fabric of quantum entanglement itself. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, suggests that every pair of entangled particles is connected by a microscopic Einstein-Rosen bridge. That would mean space-time is laced with countless invisible wormholes tying the universe together in ways we have only begun to imagine. Phantom energy and black hole reversal. Black holes are often thought of as the ultimate cosmic end states. They are places where matter collapses so completely that not even light can escape. Once something crosses the event horizon, it is lost to the universe. It is destined to drift inward until it is either crushed into the singularity or slowly radiated away by Hawking radiation over trillions of years. However, what if that is not the end of the story? What if the universe held a secret weapon? What if there was an exotic force known as phantom energy that could not only halt a black hole's inexorable pull, but also reverse it? Phantom energy is a theoretical form of dark energy, the mysterious force currently causing the expansion of the universe to accelerate. Unlike standard dark energy, which has a constant energy density, phantom energy becomes more dominant as the universe expands. It possesses an equation of state parameter W less than -1, which leads to even more dramatic and strange consequences. The most unsettling, the universe could end not in a cold fade-out, but in a big rip. This is a hypothetical scenario where galaxies, stars, planets, and eventually even atoms are torn apart by the accelerating expansion of space. Now, apply that logic to black holes. According to some cosmologists, if phantom energy exists and becomes dominant, it might have profound effects on these gravitational monsters. Under such conditions, black holes could begin to lose mass, not slowly via Hawking radiation, but rapidly through a new kind of cosmological interaction. The intense negative pressure of phantom energy could effectively suck mass and energy out of a black hole, reversing its gravitational grip until the structure destabilizes and possibly explodes. This idea is more than just an intellectual exercise. Some models, like those proposed by Pedro F. González-Diaz and others, suggest that when phantom energy falls into a black hole, it induces a negative mass accumulation, essentially an anti-feeding process. Instead of growing the black hole, the matter makes it smaller from the inside, as if space-time were uncreating it. In extreme cases, this could lead to the black hole's complete and dramatic disappearance. But the truly mind-bending part, some versions of this theory suggest that such an event might not be purely destructive. A black hole saturated with phantom energy might not just vanish. It might bounce, turning its collapse into an explosive outward-spreading event. This reversal would not only liberate the trapped matter, but it could also create a white hole, a hypothetical object that spews out all the matter and information that was once trapped in its black hole predecessor. Phantom energy could potentially transform a black hole into a cosmic spring, a source of high-energy radiation and exotic particles that shoots out into the universe. Here are some very important questions about time and cause. Would this change happen quickly or smoothly? Would it break known physics rules, or would it just make them bigger? Would the stuff that came out be the same as what fell in, or would it be changed, mixed up, or even copied? These are not just random thoughts. Some quantum gravity models, like loop quantum cosmology, already look at bounce situations like these on a universe-wide scale. These ideas say that the Big Bang was not the start, but rather a bounce after a collapse. If space-time can bounce, then maybe black holes can too. There are observational consequences, though we are far from having the tools to test them. If phantom energy does affect black holes, then their behavior should change over cosmological time. This means future observations with gravitational wave detectors or next-generation telescopes might reveal black holes behaving unexpectedly, shedding mass faster than predicted, changing their spin or vanishing without a trace. It also complicates our understanding of long-term cosmic evolution. If black holes can reverse, then the ultimate fate of the universe might be far stranger than we thought, more a chaotic dance of creation and destruction than a slow fade into darkness. This also comes with caveats. Phantom energy, if it exists at all, would violate some of the fundamental energy conditions in general relativity. It leads to instabilities and unphysical behaviors in certain models. Number error? Reverse time inside a black hole. Picture yourself falling into a black hole. Gravity, light, space-time, everything you know about reality begins to warp in strange and unfamiliar ways. Now imagine that at some point in your descent, the arrow of time reverses. Not in a metaphorical sense, not as a thought experiment, but on a physical level, seconds begin to tick backward. Effects precede causes and memories play out in reverse. This is not just a science fiction trope, it is a real, if hypothetical consequence of the mathematics behind general relativity and certain exotic models of space-time. Could time truly run backward in the extreme environment inside a black hole? First, let us set the stage. In physics, time is not a universal constant ticking forward uniformly everywhere. It is relative, deeply intertwined with space. That is why we call it space-time. General relativity showed us that time can slow down near massive objects like stars or black holes. Near the event horizon, time stretches to such a degree that a falling object seems frozen in place to a distant observer. But from the viewpoint of the object itself, it continues falling and crossing the horizon without feeling any slowdown. Inside the event horizon, however, something stranger happens. The very geometry of space-time flips. What was once a spatial dimension now acts like time, and what was once time now points in a spatial direction. This means that once you are inside the event horizon, falling toward the singularity is as inevitable as moving forward in time. You cannot escape it, just as you cannot choose to revisit yesterday. Your future is the singularity no matter what. But some theoretical models suggest that under very special circumstances, the direction of time's arrow might be reversible. This idea is supported by a fundamental principle in physics known as CPT symmetry, which states that the laws of physics should remain unchanged if charge, parity, and time are all reversed simultaneously. This principle suggests that time reversal symmetry should be a natural part of the universe. So, what is stopping it from manifesting somewhere, perhaps in the twisted interior of a black hole? Some cosmological models entertain the intriguing possibility that the Big Bang was a rebound from a previous contracting universe where time ran backward. If black holes and the Big Bang are analogous in their mechanics, both featuring singularities and extreme space-time curvature, then it is possible that black holes lead to regions of reversed time. Loop quantum gravity, in fact, hints at this possibility. As matter collapses to an extreme density, quantum effects might halt the collapse, causing it to rebound into a new expanding region, a white hole, where time flows in reverse. But what would this reversal feel like? Would you notice it? The horrifying answer is probably not. To your consciousness, things might continue to feel forward, but the physical processes underpinning your thoughts, memories, and biology would be rewinding. Imagine remembering events before they happen, breathing backward, or watching events play out in reverse as if the universe were rewinding itself. If time truly reversed, you would not be aware of it because your perception would be part of the reversal. The arrow of time is inseparable from entropy, the natural tendency for systems to move from order to disorder. A reversed arrow would mean entropy is decreasing, broken eggs reassemble, smoke returns to cigarettes, stars unburn themselves. But here is where things get complicated. Reversing time would also mean reversing causality. This raises a host of paradoxes. Could you undo decisions? Could particles inside the black hole emit radiation before they are absorbed? Could an astronaut escape before entering simply because time is moving the other way? If time were reversed locally within the black hole but not globally, in the rest of the universe, what would happen at the boundary where the two meet? Some researchers argue that these paradoxes can be resolved through closed time-like curves, paths in space-time that loop back on themselves. These curves are allowed in the mathematics of general relativity, particularly in the rotating black hole solutions like the Kerr metric. These would allow for time to loop, reverse, and overlap without outright contradiction. But whether nature actually allows such things remains to be seen. It is also possible that black holes do not reverse time in a smooth or even way. Some theoretical models of physics say that the inside of a black hole is stacked with different areas feeling time in different ways. One layer might see time going in a straight line, another might see time going backwards, and a third might see something even stranger, timelessness. Would consciousness be able to stay alive if it went into this area? In a world where time does not move, would perception still work? The hypersphere collapse model. What if black holes are not the abysses we think they are? What if they are actually bends in a place with more dimensions? This is the shocking idea behind the hypersphere collapse model. This theory says that black holes are not singularities that make holes in our universe, but the result of a collapse in dimensions we cannot even see. From this point of view, the crushing gravity and apparently endless density of a black hole are signs of something much stranger, the fabric of space in a hypersphere folding in on itself from a higher dimension. Welcome to the cutting edge of science fiction, where general relativity and higher dimensional mathematics meet. Let us talk about what a hypersphere is. In 3 dimensions, a sphere is the set of all points equidistant from a center. In 4 dimensions, that concept becomes a hypersphere. A 3-dimensional sphere can be thought of as the surface of a 4-dimensional hypersphere, just as a 2-dimensional circle can be thought of as the surface of a 3-dimensional ball. Now let us imagine that a massive star does not collapse into a singularity, an infinitely dense single point. Instead, it collapses toward the center of a hypersphere. From our limited 3-dimensional perspective, that collapse looks like a singularity, but that is only because we are seeing the projection of a process happening in higher dimensions. This model suggests that when a massive star collapses, it warps not only our local spacetime, but it also folds inward through a 4th spatial dimension. In this view, gravity is a manifestation of this higher dimensional curvature, a limited curvature that extends beyond our universe and toward the center of a hypervolume. The event horizon is the 3-dimensional shadow of this 4-dimensional object, the surface boundary of this hyperspherical structure. It is not a wall or a hole, it is the 3-dimensional shadow of a 4-dimensional object. This might sound abstract, but it could resolve several paradoxes plaguing black hole physics. For instance, the singularity problem, the idea that black holes contain a point of infinite density, vanishes in the hypersphere model. Instead of matter collapsing into nothingness, it spreads into a 4th dimension. We cannot access distributing its energy across a spatial manifold we cannot see. This not only makes the mathematics cleaner, but potentially makes black holes less violent on a fundamental level. It also redefines how we understand the information paradox. Traditionally, black holes appear to destroy information by trapping it beyond the event horizon and eventually evaporating via Hawking radiation. But if black holes are higher dimensional folds, then the information may never be truly lost. It could be encoded across the hypersphere's surface or even shifted into another dimension entirely. This aligns eerily well with holographic theories, which propose that all the information inside a black hole is encoded on its 2-dimensional boundary, a principle also born from higher dimensional thinking. Strangely enough, the hypersphere model suggests that black holes may link parts of spacetime that are in different dimensions or worlds. If spacetime is bent enough in a higher dimension, it could pinch off and reappear somewhere else. This leads to a strange but interesting idea. Maybe every black hole is actually a doorway to another part of spacetime, like a natural wormhole kept stable by the hypersphere's structure. Some versions of the model transform black holes into bridges between a contracting dimensional space and an expanding one. On the contracting side, our universe time progresses, entropy increases, and matter becomes denser. On the expanding side, which could be a different universe, the opposite occurs. Time emerges from a low entropy state, matter spreads outward, and what they perceive is a big bang. This means that our universe could be the white hole to a black hole that formed in a parent universe. That is right. Our entire cosmos could be the product of a hyperspherical collapse in another reality. This does not just change our view of black holes, it changes our view of cosmology. Black holes become nodes in a cosmic network of dimensional transitions, seeding other universes or looping matter and information through cycles of collapse and rebirth. The implications are staggering. Birth and death, creation and destruction might not be endpoints, but folds in a larger, higher dimensional pattern. We do not currently have direct evidence of extra dimensions, and most of our instruments are built to detect 3-dimensional phenomena. But the mathematics behind higher dimensional manifolds is well established, and some versions of string theory and M theory already require extra spatial dimensions for internal consistency. The hypersphere collapse idea could give those theories a visible, testable consequence, especially if it affects gravitational wave patterns or Hawking radiation in subtle ways. Could black holes be cosmic seeds? For many years, black holes were seen as the graveyards of matter and energy, a one-way ticket to oblivion. But a bold new idea has turned that narrative on its head. What if black holes are not the end of universes, but the beginning? This radical theory pushes the boundaries of cosmology, asking the incredible question, could every black hole give birth to a new universe? Could these dark, collapsing objects be cosmic seeds, destined to sprout entire new regions of space-time beyond their event horizons? To understand this, let us revisit the structure of a black hole. At its core, according to classical general relativity, lies a singularity, a point of infinite density and zero volume. But infinities are often signs that our equations are breaking down, not that nature is truly infinite. The singularity might instead represent a boundary condition, a transition point where known physics gives way to something new. If so, it is possible that instead of terminating reality, a singularity initiates a new one, a kind of Big Bang inside the black hole. This concept, sometimes called black hole cosmology, is grounded in the idea that the extreme density and curvature within a black hole might mirror the conditions of the early universe. If the Big Bang could create our universe from an ultra-dense state, why could not similar conditions in a black hole spark a new space-time region? The collapsing matter does not end. It bounces, potentially in a different direction of time or in another dimension entirely, where expansion begins anew. Some theorists, including physicist Lee Smolin, have proposed a tantalizing extension of this idea called cosmological natural selection. In this model, every black hole gives birth to a new universe with slightly different physical constants. Universes that produce more black holes generate more offspring, leading to a kind of Darwinian evolution on a cosmic scale. If true, it might explain why our universe has physical laws finely tuned for black hole formation. It is simply the result of eons of cosmic trial and error. But if black holes can start new universes, where are these children? Not in our own observable space, but somewhere else beyond the event horizon, beyond the very fabric of our reality. In this view, a black hole does not just warp space-time, it also severs it, creating a bubble universe that expands from its core. That bubble becomes a new cosmos causally disconnected from ours, with its own timeline, its own laws, and its own distribution of matter and energy. This idea resolves some paradoxes while creating new ones. It provides a beautiful potential answer to the information paradox. If all the matter and energy that falls into a black hole goes on to create a new universe, then information might not be lost, but rather transferred. The child universe could inherit the structured information from its parent universe's collapsing matter. We may never be able to access it, but its mere existence would preserve the conservation laws that black holes seem to threaten. There is no direct evidence that anything lies beyond the singularity, much less an entire universe. And many questions remain. How is the expansion triggered? What sets the physical constants of the new universe? Can any of this be tested from our side of the event horizon? These are open puzzles, but some answers may come from our growing understanding of quantum gravity and the possible structure of space-time at Planck-scale densities. Furthermore, the birth of black holes could mean that the multiverse is not composed of random universes, but rather of universes born from our own. If black holes are constantly creating new universes, and each of those universes creates its own black holes, then reality is not a single tree, but a fractal forest with branches extending in all directions through space and time. We are not at the center. We might not even be the first. This idea gives black holes a much more profound significance. They are not just interesting natural phenomena. They are creative hubs, places where space-time is being born, where gravity is forging the building blocks of new universes, hawking radiation, whispering until death. Black holes, with their immense mass immovability and insatiable appetite, seem eternal. But what if they are not? What if instead of lasting forever, these cosmic beasts slowly fade away, leaving behind only a faint whisper? That is the astonishing consequence of Hawking radiation, a phenomenon predicted by Stephen Hawking in 1974 that transformed our understanding of black holes from eternal pits to slowly dying embers. According to quantum field theory, even the vacuum of space is not truly empty. It is a seething cauldron of virtual particles constantly popping in and out of existence. Normally, these pairs of particles annihilate each other almost instantly, but near the event horizon of a black hole, something strange can happen. One particle of the pair may fall into the black hole while the other escapes. From the outside, it looks as though the black hole has emitted a particle, effectively losing mass. This is Hawking radiation, and over time it causes the black hole to shrink. What makes this truly mind-bending is that the black hole evaporates not with a bang, but with a whisper. The radiation is incredibly faint, especially for large black holes like those formed from stars. For a black hole the mass of our Sun, the temperature of this radiation is a fraction of a microkelvin colder than the cosmic microwave background. That means black holes currently absorb more energy from the universe than they emit. But in the far future, when the cosmos grows colder and emptier, Hawking radiation will become the last light in the universe. This slow leakage has profound implications for thermodynamics and information theory. In the 1970s, Hawking's discovery led to the notion that black holes have entropy, a measure of disorder or information. More massive black holes have more entropy encoded on the surface area of their event horizon. That idea forms the foundation of the holographic principle, which suggests all the information within a volume of space can be described by a theory on its boundary. But what happens to that information when the black hole evaporates? If it simply vanishes, that would violate a fundamental principle of quantum mechanics: that information must be conserved. This is the famous black hole information paradox, a puzzle that has preoccupied scientists for decades. Hawking himself originally believed that information was truly lost. He later changed his mind, suggesting that information might slowly leak out in the radiation or be encoded in subtle correlations between particles. The radiation is not just thermal noise, it could carry the memory of everything the black hole has consumed. If that is true, then, in theory, if you had infinite time and computational power, you could reconstruct the entire history of what fell into a black hole by analyzing its final breaths. It is the slowest, most mysterious form of cosmic storytelling. As a black hole evaporates, it gets smaller and paradoxically hotter. Near the end of its life, the black hole's temperature rises rapidly and its radiation becomes more intense. Some theorists believe the final moments of a black hole could resemble a tiny explosion releasing a brief, powerful burst of energy. These so-called black hole fireworks might be detectable as high-energy flashes in the cosmos if we are ever lucky enough to catch one in progress. Some even speculate that tiny black holes called primordial black holes formed in the immediate aftermath of the Big Bang. If they exist, some of them might be evaporating right now. Detecting their final flashes could provide direct evidence of Hawking radiation and offer a new window into the early universe and the nature of quantum gravity. As of now, no such events have been observed, but the search continues. Echoes from beyond. Do merging black holes ring strange bells? In 2015, humanity heard the universe hum for the first time. It was not a sound in the traditional sense. It was a ripple passing through the fabric of reality itself. More than 1 billion light-years away, two black holes merged, and the Laser Interferometer Gravitational Wave Observatory detected the shock wave of their union in the form of gravitational waves. It was a brief chirp that confirmed a century-old prediction of Einstein's, but that chirp might conceal a secret even more profound than the event itself, because some scientists believe there are echoes, strange delayed pulses that follow the main gravitational wave signal echoes that could revolutionize our understanding of black hole interiors and quantum gravity. When two black holes merge, they create a single larger black hole that vibrates as it settles into its final shape. This ring-down phase emits gravitational waves in a specific pattern like a struck bell. According to classical general relativity, this vibration should quickly fade into silence. But if the edge of a black hole is not a perfect event horizon, but instead some kind of quantum surface, a firewall, a fuzzball, or some other exotic structure, then some of those waves could bounce back and forth. They would reflect between layers near the event horizon and produce delayed repeating signals. These are the black hole echoes, faint and controversial. They would suggest that something is sitting at, or just outside the event horizon, something that breaks the traditional notion of a smooth, featureless boundary. These echoes would not be loud. They would be subtle modulations buried in the noise detectable only through deep statistical analysis and signal filtering. Some early studies of LIGO and Virgo data have claimed possible detections of these echoes, especially after the first few black hole mergers. But the evidence is still debated, with skeptics arguing the patterns could be noise or data processing artifacts. Yet the implications are enormous. If echoes exist, they could be a quantum fingerprint left behind by the new physics operating at the black hole's edge. It could mean the event horizon is not the final curtain we thought it was. Instead, it could be a membrane-like surface with its own internal dynamics, capable of interacting with the universe beyond. It could even be a place where information gets stored or scrambled, not lost. These ideas connect to the idea of black hole complementarity, which tries to explain why people looking from different angles see different things. Someone falling into the black hole sees nothing special at the horizon, but someone looking from the outside sees information spread out on the surface. It is possible that echoes are the middle ground, proof that at the barrier something real, measured, and different is happening. Echoes can also be caused by other things. In new models of gravity, the shape of space-time around black holes might make room for more gravitational modes or extra dimensions that change the way waves travel. Some of these ideas say that there will be ringing effects that are not linear, which are strange behaviors that Einstein's equations do not explain. One of the few direct ways we could test these ideas would be with echoes. Even if the echoes turn out to be illusions, the very search for them has pushed the limits of gravitational wave astronomy. Scientists are developing more sensitive algorithms and cleaner data analysis tools to comb through signals looking for any sign of the unexpected. As detectors like LIGO, Virgo, KAG-ray, and soon LISA expand our reach, we will collect more and more black hole mergers, increasing our chances of catching genuine anomalies. Some physicists suggest going even further. Rather than just waiting for natural black hole mergers, we could simulate ringdowns and search for echo-like behavior in lab-based analogues. Certain condensed matter systems and fluid dynamics experiments can mimic aspects of space-time curvature, allowing us to model how echoes might behave without the need for billion solar mass collisions. Are black holes conscious in any way? It sounds like the plot of a science fiction novel, an ancient invisible giant floating through space, silently consuming stars and perhaps somehow aware of it. The idea that a black hole might possess a mind is on the thin line between theoretical physics and radical philosophy, but it is more than just a cosmic daydream. As the universe continues to blur the line between information and matter, it is a legitimate thought experiment to ask whether a black hole might exhibit some form of awareness, or at least a primitive form of consciousness. First, let us be clear. No physicist seriously believes a black hole is thinking in the way humans do. There is no brain, no neurons, no centralized organ organizing sensory input. But modern science has repeatedly shown us that consciousness might not need a brain, at least not in the way we traditionally define one. Some theories, particularly in the realm of quantum cognition and panpsychism, suggest that consciousness could be a fundamental property of matter, much like mass or charge. In this view, everything down to the most elementary particles possesses some level of experiential knowledge. This does not mean a quark knows your name. It means that the building blocks of experience might be woven into the fabric of reality. And if this is true, then black holes as the most extreme physical structures in the known universe might be the most extreme manifestations of that deep knowledge. Let us look at some ideas. There is the integrated information theory developed by neuroscientist Giulio Tononi, which proposes that consciousness arises from systems that can integrate vast amounts of information. In simpler terms, a system is conscious when it can process information in a deeply interconnected way like the human brain. Strangely enough, black holes are massive repositories of information. They obey the laws of entropy, possess maximum information content, and may process that data in a quantum way we do not yet understand. Does that qualify as a form of consciousness under IIT? Then there is the black hole information paradox, which poses the question, if information falls into a black hole, is it truly lost? Hawking's original calculation suggested it was violating quantum mechanics. But later theories, including black hole complementarity and the holographic principle, argue that information is actually encoded on the event horizon like a two-dimensional shell, storing everything that fell in. This horizon behaves almost like a memory surface, and some physicists have gone so far as to suggest that black holes may compute in strange, entangled ways. In this speculative landscape, it is not such a leap to ask if a black hole stores, scrambles, and possibly processes information. Might it also experience it in some unfathomable way? Consciousness, as we understand it, is inseparable from the flow of time, and black holes deeply distort time itself. For an object falling into a black hole, time slows to a crawl. From a distance, the object appears frozen. From within, it races toward the singularity. If experience is bound to the perception of time, then a black hole represents an ultimate crucible, a place where time, and thus consciousness, may be stretched, shredded, or even redefined. Could black holes act as cosmic observers? Some interpretations of quantum mechanics suggest that the act of observation or measurement is what causes a quantum system to collapse into a definite state. If black holes interact with quantum fields, absorb particles, and alter the flow of information, are they, in some sense, observing the universe? And if observation is at the heart of consciousness, is there a dim, flickering light of awareness? At the center of these galactic behemoths, there is no doubt that the complaints are accurate. Since black holes do not have a nerve system or any known way to receive sense information, calling them conscious is at best anthropomorphic. But that is not the point. The point is to see if the conditions of black holes, especially in terms of information theory, complexity, and energy gradients, might be similar to any known structure of processing that is intelligent. White holes, the exploding mirror image. If black holes are the great consumers of the universe, inhaling light, matter, time, and even information, then white holes are their hypothetical opposites, impossibly bright engines that can only spew energy outward. Predicted by the same mathematics that foretold black holes, white holes are like cosmic fountains ejecting matter with such violence that nothing can enter. While they remain unproven, they are more than just a sci-fi fantasy. They might hold the key to resolving some of the deepest mysteries about black holes, the arrow of time, and even the origin of our universe. The concept of a white hole emerged from Einstein's general theory of relativity. When Carl Schwarzschild derived the first black hole solution in 1916, the equations also allowed for a time-reversed version 1, where instead of a singularity pulling everything in it, violently ejects matter outward. But this was not just a symmetrical curiosity. In theory, a white hole is connected to a black hole through a tunnel known as an Einstein-Rosen bridge, better known to most of us as a wormhole. This wormhole structure, however, is incredibly unstable. Any amount of matter, even a single photon trying to enter the white hole side, would collapse the tunnel. It is like trying to walk into a volcanic eruption. The force pouring out is so intense there is no going in. That makes white holes fundamentally different from any other object in physics. They are visible unlike black holes, but completely unreachable, forever retreating from interaction. So, where are they? Why have we not seen any? One reason is that if they exist, white holes might be incredibly short-lived. Some theories suggest they only manifest at the end of a black hole's life. Over trillions of years, a black hole slowly evaporates via Hawking radiation. But instead of simply vanishing, the black hole might go out with a final burst of energy, creating a white hole that ejects all the information it once consumed. This idea provides a potential solution to the black hole information paradox. Instead of being destroyed, information is delayed, hidden, and then released at the end of time. In this view, a white hole is the final breath of a dying black hole, a quantum bounce, instead of a collapse. This idea is supported by loop quantum gravity, an alternative to string theory. It suggests that inside a black hole, space-time hits a kind of quantum barrier and bounces back, transforming the black hole into a white hole instead of a singularity. Think of falling into a black hole not as an end, but as the beginning of an explosion in another region of space-time. This brings us to the tantalizing idea that our universe might be the interior of a white hole. If a black hole in a parent universe bounced, the explosion on the other side could look a lot like our Big Bang. That is right. We could be living inside a white hole's event horizon, forever expanding from its initial ejection. This theory, while still speculative, offers a possible explanation for why our universe has such low entropy at its birth and a uniform expansion traits that standard Big Bang cosmology struggles to fully explain. Another idea connects white holes to dark matter. If primordial black holes formed in the early universe and underwent quantum bounces, their white hole remnants might still be floating invisibly through space, contributing to the unexplained mass we observe. These black to white hole transitions would be faint, silent, and hard to detect, but not impossible. Some fast radio bursts or unexplained gamma-ray bursts could be clues. What is the catch? No one has seen a white hole directly. There are huge problems with every theory that involves them in terms of math observations and ideas. General relativity lets them happen, but quantum physics makes it hard to tell how stable they are. Still, just like black holes were once thought to be mathematical oddities, white holes might one day go from being a theory to something we can actually observe. That could happen especially if we become better at detecting high-energy cosmic blasts or quantum echoes, dark matter black holes. For decades, dark matter has been one of the biggest mysteries in astrophysics. It is a mysterious form of matter that does not emit light or interact with normal atoms, yet it exerts a powerful gravitational influence on galaxies. But what if part of this puzzle is hiding in plain sight, not in the form of exotic particles, but in the form of ancient black holes? The idea that some of the universe's dark matter could actually be composed of black holes is one of the most intriguing and controversial theories in modern cosmology. These are not your typical stellar mass or supermassive black holes formed from dying stars. They are called primordial black holes, and they may have formed in the chaos of the early universe long before the first atoms or stars existed. In the moments after the Big Bang, when the universe was unimaginably hot and dense, regions of space-time could have undergone extreme fluctuations in energy. If those fluctuations were intense enough, they could have caused certain pockets of space to collapse under their own gravity, forming black holes instantly. These primordial black holes would not need stars to form, and they could be incredibly small, ranging in mass from that of a mountain to that of the Earth or beyond. Crucially, they could have survived until today, quietly roaming the cosmos, invisible to telescopes, but detectable through their gravitational effects. So why have we not found them? In part because they are incredibly hard to detect. They do not emit light, they do not interact electromagnetically, and unless they pass through or near something with enough mass like a star or another black hole, they leave no trace. But scientists have proposed several clever ways to spot them. One method is gravitational microlensing, where a black hole passes in front of a distant star and temporarily magnifies its light due to gravity. Several microlensing events have been recorded over the years, and some researchers argue that a few of them could be evidence of primordial black holes. Another possible clue comes from LIGO, the Laser Interferometer Gravitational Wave Observatory. In recent years, LIGO has detected several black hole mergers involving objects with masses that do not quite fit the standard models of stellar collapse. Some of these black holes are too small, too large, or in binaries that should not exist if they were formed from stars. Could these be ancient primordial black holes finally merging after billions of years? It is a hypothesis that is gaining attention. Another thing is the matter of plenty. Dark matter makes up about 85% of all matter in the universe. These primordial black holes would have to be very common and spread out to explain all of this matter. Some models suggest a mixed approach in which these unseen black holes only make up a small part of dark matter, and other strange particles like WIMPs or axions make up the rest. But there are some problems with the idea. It is likely that there would be more lensing events, more disruptions of star systems, or even more radiation from Hawking evaporation in smaller black holes if there were too many primordial black holes. It is actually very hard to say how common these black holes are based on data from the cosmic microwave background and gamma-ray instruments. It is still only true in a small window though, and scientists are working hard to find that gap. It is interesting that primitive black holes might be able to explain more than just dark matter. They might be great places to try ideas about quantum gravity, the early universe, and even the multiple universes. Some models even say that the supermassive black holes we find at the centers of galaxies today may have been started by a primordial black hole. This would be like a cosmic snowball effect that began with very small black dots. Black hole chemistry. When you think of chemistry, you probably do not picture the infinite void of a black hole. You likely imagine bubbling beakers, periodic tables, and molecules bonding in a laboratory. But emerging theories suggest something remarkable because black holes so closely follow the laws of thermodynamics, they may behave like chemical systems. This is not just an analogy. Scientists are now actively exploring black hole chemistry, a field that suggests these cosmic objects have measurable properties like pressure, volume, temperature, and even phase transitions, all hallmarks of classical chemistry and physical systems. These gravitational behemoths might behave more like cosmic molecules than we ever thought possible. This strange connection began with the discovery that black holes have entropy. Thanks to the work of Stephen Hawking and Jacob Bekenstein in the 1970s, we now know that black holes emit a faint thermal radiation called Hawking radiation. Their entropy is proportional not to their volume but to their surface area. That simple insight led to a cascade of revolutionary ideas. In classical thermodynamics, entropy is central to understanding how systems evolve, and if black holes obey the same rules, then perhaps they are not exempt from the ordinary processes of heating, cooling, and even boiling over into new states. This is the idea of black hole phase transitions. Just like water can boil into steam or freeze into ice, certain types of black holes, especially in anti-de Sitter space, a kind of mathematical universe used in theoretical physics, can also change their state. They appear to undergo transitions depending on their temperature and pressure. In some configurations, black holes might exist in a small state or a large state, with transitions in between that mirror the behavior of everyday matter. This is particularly intriguing in the context of charged black holes like the Reissner-Nordstrom black hole. They show behaviors analogous to van der Waals gases, the kind described by the ideal gas law, but with added complexity due to molecular attraction. Black holes may have a chemical potential, which is a strange idea that says they want to change, take, or send matter and energy out into space. This changes how we think about a black hole's mass. It is no longer just a fixed amount of matter. It is now something that moves and reacts to its surroundings. Equations about the cosmological constant, which shows how densely charged empty space is, also led to the idea of black hole pressure. If the cosmological constant can change, then black holes live in a world where pressure can change, which would make their thermodynamic behavior different. In a bigger thermal system, a black hole is like a complicated particle that is always changing. These concepts do more than just make black holes interesting. They hint at a deeper unification of physics. The idea that gravity, thermodynamics, and quantum mechanics might all share a common foundation is one of the holy grails of theoretical physics. If black holes follow the rules of chemistry, then studying them could unlock clues about how these three great pillars of science fit together. It might even provide a pathway toward quantum gravity, the long-sought theory that explains gravity at the smallest scales. Black hole chemistry is, in this view, a kind of Rosetta Stone, a key to translating between seemingly unrelated areas of science. This field affects more than just academic discussion. It also changes how we understand what gravitational wave monitors are telling us. When two black holes merge, they might send out signs that show not only their mass and spin, but also changes in their physical state. If black holes can change phases, then these changes could cause gravity wave patterns to change in small ways. People are becoming more interested in this idea, but it is still very much a guess. And if it turns out to be true, we might be able to listen to black hole science in motion. One day, black hole chemistry could one day be used to simulate strange materials, create new quantum methods, or test ideas in the field of high-energy particle physics. Researchers could use it to make better models for quantum information theory, or to look into how the world started out using entropy models. To put it another way, learning about the science of black holes might not just help us understand faraway celestial bodies, it might also help us learn about technology, computers, and matter itself. Entropy area and the Bekenstein bound. In physics class, we first learned about entropy as a way to measure disorder, the number of ways a system can be arranged without changing its observable state. But when it comes to black holes, disorder takes on a much deeper, stranger role. The idea of black hole entropy, pioneered by Jacob Bekenstein and expanded upon by Stephen Hawking, completely revolutionized how we think about information and the physical limits of reality. At the heart of this revolution is a remarkably simple idea. A black hole's entropy is proportional to the surface area of its event horizon, not its volume. The Bekenstein bound is a theoretical limit on how much information or entropy can be contained within a given region of space. It was based on that idea. This principle might sound abstract, but it has profound implications. Normally, we assume that the more volume we have, the more stuff we can pack in, more books in a bigger library, more atoms in a larger box. But in black hole physics, that logic collapses. Instead, the amount of information that can be stored in a region of space is capped by the area of its boundary, measured in Planck units, the smallest possible units of space and time in physics. That is like saying a computer's memory does not depend on its internal volume, but only on the size of its screen. The larger the screen is the surface area, the more data it can theoretically store. This discovery called into question one of our most deeply held assumptions, that space is fundamentally three-dimensional. The Bekenstein bound and the area-entropy relationship led some physicists to believe that the universe might be a kind of hologram. In other words, all the information that makes up our perceived three-dimensional reality could be encoded on a two-dimensional surface. This is like how a holographic image on a credit card stores a three-dimensional illusion in a flat piece of film. This is the basis of the holographic principle, one of the most powerful and wild ideas in theoretical physics. It is now a cornerstone of efforts to unify general relativity and quantum mechanics. This idea comes to life in a big way when it comes to black holes. Picture putting a book, a memory card, or even a whole planet into a black hole. Where does the information about that object go? The laws of quantum mechanics forbid the loss of information. But general relativity says that once an object crosses the event horizon, it is gone for good. The Bekenstein bound provides a solution. The information is not lost, it is encoded on the surface of the black hole, As the object falls in the surface area of the event horizon increases by a tiny amount, just enough to accommodate the new information. This does not just apply to matter, it applies to every physical process. The growth of a black hole, its merger with another, or its evaporation via Hawking radiation, all must preserve this intricate accounting of entropy. The second law of thermodynamics, which states that the total entropy of an isolated system must increase or stay the same, is upheld, but in a form so alien that it rewrites the very geometry of the cosmos. The Bekenstein bound is not confined to black holes. It theoretically applies to any system with a finite amount of energy and a confined volume. If you tried to cram too much information into a given space, you would eventually create a black hole. Thus, the Bekenstein bound also sets a hard cap on computation and memory storage. There is a physical limit to how much a quantum computer or any digital system could store in a given area, making this concept relevant not just for cosmic theorists, but potentially for future engineers and data scientists. Moreover, this area-based entropy has been tested in string theory and various models of quantum gravity. In nearly all of them, the result is the same: black holes obey thermodynamic laws. They have temperature, entropy, and energy, just like a cup of coffee cooling on your desk. Only in this case, the cup is a boundary between reality and mathematical madness. The more we understand this limit, the more it seems that entropy and information are not side players in physics. They may be the fundamental building blocks of reality itself. The information cloning problem, one of the most fascinating questions in modern science, is not whether a person can survive falling into a black hole, but whether information can. According to quantum theory, information cannot be lost. Every particle, state, and relationship in the universe contains information about its history, and that information in principle should be conserved forever. But general relativity presents a very different picture. Anything that falls past the event horizon of a black hole appears to be permanently and irretrievably lost. The conflict between these two ideas, one of conservation and memory, the other of loss and forgetfulness, gives rise to the famous black hole information paradox. But there is another twist in this tale. What if black holes do not just destroy information but illegally copy it? This is the heart of the information cloning problem, a violation of the quantum no-cloning theorem. According to this principle, it is impossible to create an identical copy of an unknown quantum state. This rule preserves the uniqueness and integrity of quantum systems. But black holes in their mysterious way may be doing something stranger. When information falls in, it may become imprinted on the event horizon, encoded in what physicists call soft hair or surface area states. At the same time, quantum mechanics insists that the original information must remain intact in some form. This opens up a disturbing possibility: two versions of the same information, one inside the black hole and one smeared across the event horizon, and that would break the rules. In the real world, cloning would make it impossible to understand quantum computers' encryption and even the idea of cause and effect. Imagine being able to copy the state of a basic particle or a quantum key. You would weaken information security and make it possible for paradoxes to happen. Since black holes seem to be able to do this, either quantum theory is not complete, or we have the wrong idea about what a black hole is. A number of proposals have been put forward. One is the complementarity concept, which suggests that no single observer can ever see both copies of the information at the same time. For an observer outside the black hole, the information never truly enters. It is stored on the horizon and slowly leaks out via Hawking radiation. For an observer who falls in, the information continues on its journey inside to be lost in the singularity. Both realities are true, but no one can access both at the same time. This view gets around the problem of cloning by changing what it means to know a state based on your point of view. Then there is the more radical approach. Maybe the information never enters the black hole at all. The firewall hypothesis proposes that a searing wall of energy burns up incoming data just outside the horizon preserving information but destroying the notion of smooth passage into the black hole. In this view, the idea of a gentle fall across the event horizon is a myth. Reality is shredded just before you ever get there. Again, no duplication, just annihilation with memory preserved. The holographic principle may, however, offer the most interesting answer. If a black hole's three-dimensional volume can be described by a two-dimensional surface theory on its boundary, then information might not be copied after all. It might just be represented in two different ways. You are not seeing two different things. You are seeing two sides of the same thing, like looking at a three-dimensional object from two different angles. In this way, quantum theory, relativity, and the no-cloning theorem would all be saved. The problem of cloning will not go away. What happens when two black holes merge? Do the information contents of two event horizons combine, cancel, or reinforce when they meet? What about Hawking radiation? Does it carry only scrambled pieces of the original, or does it carry exact copies? If scientists ever develop instruments sensitive enough to decode Hawking radiation, will they find duplicate bits of information emitted before the black hole evaporates? The black hole as a quantum computer. Black holes are not just massive gravitational pits. They may be the universe's most powerful computers. This is not a metaphor, but a very specific scientific hypothesis. Some researchers on the cutting edge of theoretical physics and quantum information theory suggest that black holes may be able to process information in a way that is analogous to a quantum computer. Black holes might not just store the information of the objects they consume. They might also compute with it, transforming it, scrambling it, and perhaps even solving problems that are intractable for humans. It begins with the idea that black holes have entropy, an astronomical amount of it. The Bekenstein-Hawking formula links a black hole's entropy to the surface area of its event horizon, measured in Planck units. This implies that every tiny patch of that surface encodes a bit, or more accurately, a qubit of information. When matter falls into a black hole, its quantum state becomes part of this sprawling, dynamic boundary. But that data does not just sit there. It evolves, and that evolution is governed by the same kind of unitary operations that define quantum computation. In this view, the information paradox is completely reframed. Black holes are no longer seen as places where information is lost or even just stored. Instead, they are viewed as information processors. They take in quantum information, transform it through complex operations analogous to quantum logic gates, and then emit the results in the form of Hawking radiation. If this is true, black holes are not just archiving data, they are performing calculations with it. The Hayden-Preskill protocol gave the idea a big boost. It was a thought experiment that showed a black hole could start releasing new information amazingly quickly, as long as it is already highly entangled with information it has already released. This suggests that black holes act as fast scramblers, systems that rapidly mix information so thoroughly that even a small output can reveal a great deal about the entire input. This is similar to how a good encryption algorithm or a quantum circuit works. This leads to an unexpected intersection with complexity theory. Some theorists propose that the longer a black hole exists, the more complex the quantum state of its horizon becomes. In this view, black holes are complexity engines evolving towards states that are nearly impossible to reverse despite being unitary in principle. This could explain why, even though information is not lost, it is so deeply scrambled that recovering it is practically impossible without exponentially advanced tools. The implications are profound. Is it possible that the universe is a form of quantum computation? Are black holes the processors quietly running cosmic code? Could we read the information encoded in Hawking radiation if we knew their programming language? It would be like solving the ultimate cosmic puzzle. Some researchers are already working hard to make this dream a reality. Some theoretical models, such as the SYK model and the ADS, divided by CFT duality, look at black holes as quantum systems in the real world. Quantum simulation and tensor network experiments try to model these systems on very small levels to see if they can copy the entanglement structures we think exist at the edges of black holes. Firewalls versus fuzzballs versus freefall, the battle for the interior. The interior of a black hole is a battleground of ideas, a place where our most fundamental theories collide, creating paradoxes that threaten the very foundations of physics. For observers, we have traditionally pictured the event horizon as a smooth transition. If you fell in and somehow survived the tidal forces, you would pass through seamlessly into the black hole's dark heart. But quantum mechanics does not like that story. It demands that information must not be lost. And so three competing ideas for the black hole interior have emerged: firewalls, fuzzballs, and freefall. Each one offers a radically different vision of what truly happens when something crosses a black hole's boundary. They all attempt to answer the same question: what is it like inside a black hole? First, let us look at the most dangerous option: firewalls. Instead of a smooth passage, the firewall hypothesis proposes that a wall of high-energy particles exists at the very edge of the event horizon. This is thought to solve the black hole information paradox. Any object or observer that fell in would be instantly incinerated. This idea arose from the AMPS paradox, named after Almary Marolf Polchinski and Sully. It argued that preserving quantum unitarity and avoiding information loss comes at a terrible price: the breakdown of Einstein's equivalence principle. If firewalls exist, then the most fundamental idea in general relativity, that nothing special happens at the horizon, is violated. You would not just float past the event horizon, you would hit a quantum death trap. Now consider fuzzballs, a concept rooted in string theory. According to this idea, black holes are not empty voids with singularities at the core. Instead, they are composed of tangled, vibrating strings entirely filled with quantum fuzz. There is no traditional interior, no singularity, and no event horizon as we usually understand it. Rather, all the mass and information of a black hole is spread out across this tangled mass of strings. What appears to be an event horizon is just the outermost layer of fuzz. Nothing falls in because there is no in. You hit the fuzz and merge into its structure. Fuzzballs preserve information not by encoding it on a horizon, but by never allowing it to fall in to begin with. Then there is freefall, the classic view inspired by general relativity. According to this picture, the event horizon is completely benign for the infalling observer. You pass it without noticing anything unusual. From your perspective, gravity intensifies, time distorts, and you eventually spiral into the singularity. All the mysteries, firewalls, fuzzballs, information puzzles are either irrelevant to your journey or only arise when viewed from the outside. This model defends the idea that Einstein's equivalence principle remains intact. Locally, the laws of physics do not betray you even when you are falling into one of the universe's most extreme environments. How do we choose the right view? That is the real fight, and it is still going on. People who support barriers say that without them, unitarity and quantum theory fall apart. The fuzzball camp says they fix the problem by coming up with a new way to think about black holes. Freefall supporters, on the other hand, think that firewalls are too extreme, and that the problem comes from trying to mix ideas that do not go together too literally, at least not yet. None of these ideas have been proven by experiments. We cannot get near enough to a black hole to send a probe in and hear what it does. But evidence on gravity waves from black holes merging and better models of Hawking radiation may tip the balance in the long run. For example, if we find echoes after black holes merge slight changes in space-time that do not fit with what we know about general relativity, they could be signs of quantum structure at or near the event horizon. That might help firewalls or fuzzballs work better. Another angle comes from quantum entanglement. If Hawking radiation is entangled with its source and new radiation is also entangled with past radiation, you eventually reach a contradiction known as the monogamy of entanglement. Resolving this is what gave birth to firewalls in the first place. But string theorists argue that fuzzballs already resolve this contradiction naturally. There is no need for entanglement across a horizon if there is no traditional horizon to begin with? Black holes in extra dimensions. What if black holes are not what they seem to be? What if space is bigger than we think? That is the idea behind one of the most daring and strangest theories in theoretical physics, the existence of extraspatial dimensions. Everyday life takes place in 3 dimensions of space, left to right, up and down, and forward and backward. But some of the most advanced models of physics like string theory and M-theory suggest the universe has more. 6 or 7 hidden dimensions might be rolled up so tightly that we do not even notice them. And if these dimensions exist, black holes, as the most extreme gravity laboratories we have, might behave in profoundly different ways within them. One of the earliest signs that extra dimensions could affect black hole physics came from the so-called brain-world scenarios. In these models, our familiar universe exists on a 3-dimensional membrane or brain, floating in a higher dimensional space known as the bulk. Gravity, unlike light or matter, can leak into these extra dimensions. That means black holes might not confine their mass and curvature to our 3-dimensional slice of reality. Their gravitational influence could stretch deeper into the hidden bulk, changing how they form, grow, and even evaporate. In extra-dimensional space, the very shape of a black hole could change. Instead of being perfectly spherical or ring-shaped, like a Kerr black hole, higher-dimensional black holes could resemble bizarre objects, such as black strings or black brains, elongated, stretched-out forms extending in unseen directions. Some theories even propose toroidal black holes shaped like donuts. These shapes are more than just curiosities. They dramatically alter the mathematics of space-time curvature and could even make black holes unstable in ways we would never expect. In higher dimensional models, black holes radiate differently. More dimensions mean more channels through which radiation can escape, speeding up the evaporation process. A microscopic black hole created in a high-energy collision like those at the Large Hadron Collider might last mere fractions of a second before disappearing in a flash of particles. That is why some physicists once thought the LHC could create tiny black holes, not dangerous ones but evaporating ones that could reveal the fingerprints of extra dimensions. But how would we actually detect such black holes or the existence of extra dimensions through them? One method might involve gravitational waves. Black hole mergers like those seen by LIGO and Virgo emit ripples in spacetime. If extra dimensions exist, the structure of these waves might subtly deviate from predictions made by 4-dimensional general relativity. We might see additional ringing modes or energy leakage into the bulk. So far, we have not detected those signs, but our instruments are improving, and future detectors like LISA could probe these possibilities more deeply. Entropy and thermodynamics give us another view. Normal general relativity says that the entropy of a black hole is equal to the size of its event horizon. The ratio of surface to volume changes in higher dimensions, though. The rules of entropy scaling do not work as they should and change in strange ways. Some scientists think this could help us understand some of the most puzzling things about quantum gravity, like why information might stay the same, how black holes store information, and how space-time geometry forms from entanglement. The ADS divided by CFT correspondence is an interesting idea that came about from thinking about space-time outside of dimensions. It is a mathematical symmetry where a gravity theory in a higher dimensional space is the same as a quantum field theory without gravity in lower dimensions. This holographic principle says that quantum interactions on a boundary in a lower dimension can fully describe black holes in higher dimensions. Saying that a 3-dimensional object can be fully recorded on a 2-dimensional surface is the same thing. This idea changes how we think about space mass and even reality itself. Extra dimensions might also allow for entirely new classes of black holes, such as those formed not from collapsing stars, but from the geometry of space itself. These topological black holes could be stable in ways we do not yet understand, and might even contribute to dark matter. If they exist, their gravitational influence could be scattered throughout the cosmos unnoticed, because their effects stretch across dimensions we cannot observe directly. Cosmic chords. Could black holes be musical instruments of space-time? What if the universe is a symphony, and black holes are its deepest, most powerful instruments? This may sound romantic or fanciful, but there is real science suggesting that black holes vibrate, ring, and echo in ways that are deeply analogous to musical instruments. These are not metaphors. They are real, calculable physical effects that emerge from the very fabric of space-time. And if we learn to listen carefully, these cosmic chords could become one of our most powerful probes into the nature of reality. The first time humanity truly heard a black hole was in 2015 when LIGO detected gravitational waves from the collision of two black holes. The resulting waveforms, when converted into sound, produced a rising chirp, a literal echo of the final moments before the two merged. But beyond that chirp lies a subtle and complex aftermath, a phase called the ringdown, where the newly formed black hole vibrates as it settles into a stable shape. These vibrations are called quasi-normal modes, and they are the black hole's natural frequencies, just as a bell rings at specific pitches, depending on its size and shape. Each black hole, depending on its mass, spin, and charge, has its own unique set of quasi-normal modes. The curvature of space-time around a black hole essentially gives it a musical key, and just as you can identify an instrument by its unique timbre, scientists can determine the properties of a black hole by analyzing these ringing patterns. This is the field of black hole spectroscopy, and it is rapidly becoming one of the most important tools in astrophysics. By detecting multiple modes in a single event, we can test Einstein's general theory of relativity with unprecedented precision. Or we might find new physics hiding in the harmony. But the music could go even further. Some theoretical scientists think that these quasi-normal modes might be important to how black holes process and distribute information, not just for test purposes. You can think of black holes as thermodynamic things with entropy and temperature. The way they move could represent the data they hold. So black holes might not only sing as they die, but also as they remember things, harmonics of gravitational waves. On a piano string, there is a fundamental tone and a series of overtones. It is possible that black holes' gravitational wave signals also exhibit harmonics. These overtones could become prominent in mergers with very large mass ratios, or in collisions whose geometry twists space-time into more exotic shapes. Detecting these harmonics could reveal deeper patterns in space-time, perhaps even signatures of extra dimensions or quantum gravity. But black holes may not be limited to playing the aftermath of collisions. Some researchers speculate that rotating black holes surrounded by disks of infalling matter might generate continuous vibrations, similar to how a bow drawn across a violin string creates a sustained tone. These potential space-time oscillators could emit low-frequency gravitational waves indefinitely. If so, they might act like massive cosmic tuning forks resonating across the universe for billions of years. There is also a radical idea that ties this all together, the notion that the universe itself may be fundamentally musical in nature. In string theory, all particles and forces arise from tiny vibrating strings. The frequency of a string's vibration determines the kind of particle it represents, massive, light-charged, or neutral. In this view, black holes might represent the deepest, most intense vibrations of these strings, super-resonators, where quantum and gravitational forces blend into one. Their ringing is not just an accident of physics, it is a window into the deepest structure of reality. Could it be that by mapping the vibrations of black holes, we are tuning into the sound of the universe, thinking, could gravitational wave astronomy evolve into a kind of cosmic acoustics, where listening becomes a new method of discovery? If you have made it this far, good job. You have survived the theoretical deep dive into the universe's most enigmatic objects. Black holes are not the end of the story. They are the place where the greatest questions in science converge. They can be eternal voids or quantum gateways, vibrating fuzzballs or echoes of cosmic memory. The more we learn, the stranger it gets. The next generation of telescopes, quantum theories, and gravitational wave detectors may finally unlock the interior of black holes with the help of mathematics and light. There are edges where reality breaks time, folds and space sings that you want to keep chasing.